Let me introduce our first speaker, Lynn Cherney. So Lynn Cherney is going to be talking about text toys and glitch poetics. So Lynn has a PhD in linguistics from Stanford. She's worked on research in text-based virtual worlds, MUDs or multi-user dungeons, and chat interfaces. She's been in the industry as a UX designer and a data scientist for a bazillion years now, and has been at companies such as Adobe, MathWorks, TiVo, Autodesk, and she's been working on a poetry generation algorithm for the UK Dubai Pavilion, and basically consults at Google Arts and Culture right now, where she's released a small game illustrated by AI-generated images. So Lynn has been doing talks and keynotes on creative AI projects at EuroPython, PyData conferences, and my personal favorite is she runs a newsletter, which you guys should all probably subscribe to, which has a very interesting mashup of folklore, AIR, NLP, games, and narrative links. So with that, Lynn, take it away.
Super. I have to figure out how to use this thing. Okay, so if I do that. Can you guys see my screen okay with the slides?
Yeah, I see you.
Okay.
Yes.
Yeah, and you see the slides. Okay, yeah, I don't have two monitors here. Okay, so the slides are online in case I have any network problems. Ghostweather.slides.com, you can find them under, but hopefully we'll be fine. All right, well, so Raj just did this. I think more relevant to today is that, like, I guess my artist statement, if I had a practice, would be that I come from television fandom, something not a lot of people know, and I hung out and built a lot of stuff in MUDs when I was supposed to be doing a dissertation, which is why my dissertation turned into being about chat online. I want to talk about the fan thing, though. So one of the things I did when I was in grad school was I made a lot of fan videos, which were essentially remixes of TV shows set to music, often focused on presenting a non-straight view of the show, like what we'd call slash fiction, slashing two characters, Kirk and Spock or whatever. And I also wrote stories like that. So I put the characters in other universes. Kirk and Spock are baristas in Brooklyn, and made them gay. This is not relevant because I'm going to talk about this per se, but because essentially I come from remix culture. And that's kind of what I'm interested in terms of making stuff. Remixes in the music industry are adding things from another source, deleting things from something that you don't like, distorting things, recutting, redoing for another audience. This is kind of like the theme that I keep coming back to all the time in lots of the things I make. Also, I'm interested in this sort of continuum that Chris Crawford talks about a bit between story and toy, where games are somewhere in the middle with goals. I'm often more interested in toys, frankly. Even when I play games, I'm more interested in sort of the exploration and the toy aspects than I am in, you know, catching coins or whatever, shooting people. I'm a narrative gamer person, personally. So the things I like to make in my spare time, which is not a lot right now, but I like making games into stories and poems. I like turning stories and poems into toys that are interactive, and making toys that support story and poem and generation of games. Writing this talk was kind of a weird, like, what do I care about? And it's kind of these activities. And the other thing is that, like, to do these things, you need a bunch of tooling, and the tooling is hard and difficult, especially right now for someone like me who's interested in AI models, like most of you are. Also, the user interface side is increasingly difficult. The JavaScript world and framework world is a horror show. APIs to access giant models. There are some companies that only allow access by API and others that don't at all. I'm going to talk about both those companies. Data sets and annotations. We all know that this is a giant issue in model creation. It's especially an issue in creative outputs. And creating your own custom models, even bigger problem because of the compute needed and cost. So to kick this off, I'm going to talk about a couple disappointing projects of mine. These are projects I found personally disappointing and why I found them disappointing before we talk about things I think are more interesting. So the first one was something I did internally for Google Arts and Culture that was an experiment. This castle does not exist. So I love castles, like I obsessively like castles, and I'd like to generate them and make them in many, many tools. A couple years ago, I trained a StyleGAN2 model on using the Church's LSUN dataset model that was already trained. I tuned it on images of French castles. And then I used GPT-2 tuned on Wikipedia articles about them, like the history, the architecture, whatever. And the results were good. I mean, they were, for the time, they were really good. They were actually too good. So this is a real problem if you like to make things that are fun. This is an example, like the picture on the left, it could almost be like an oil painting of a ruin, right? And the text on the right is the GPT-2 output, including a fake name, I think, although some, it plagiarized sometimes. So sometimes they were not as fake as they should have been. So there's an architecture section. There are no known plans to rebuild the castle, ownership section. It's funny, in the ownership section, which is fake text, obviously, the deed of gift stated that the castle was to be fully restored and filled with beautiful gardens. So there's definitely irony here, given that there's no known plans to rebuild the castle. But you have to read sort of closely to see that and to think it's funny. This is one of the ones I thought was better in terms of being an interesting read, but it's also crazy. Like it's the classic GPT-2 and sometimes 3 word salad kind of thing. There's like a folk story in the middle here. The basin gushes red blood after every flood, which thumbs up, like that's good. Then there's like prophets, struck by lightning, doves, column where Sebastian stands alone, 3 prophets placed in their place, statues of 3 geese symbolizing faith and prophets. I mean, it's word salad craziness, but kind of fun. So I didn't think that project was actually that great because it was a little bit boring and hard to find the fun parts. We kind of abandoned it. And this is another project that suffers from kind of a similar problem, but from an entirely different direction. This is a project I did for NanoGenma last year where I wanted, or 2 years ago now, I wanted to do data to text where I would take the database created during creation of a Dwarf Fortress world, the legends file, and turn that into a story. I've done this effort a couple of times now. And I have finally, I think, understood why it's so bad. I think if I use GPT-3, I might improve it. But basically, without using any generated text, I end up with these like very boring narrative factual accounts. So this is somebody was a male human, lived for 220 years, largely unmotivated. He had no skills. This is, based on the stats in his profile. He never had kids. That's me adding the unhappily to give it some color. He was a member, blah. Okay, so then this is a bio generated where I added the red. This is one that raises lots of questions to a reader, but the text generator doesn't know enough about the fact that this is strange to do anything interesting with it, because that requires some like world knowledge beyond the capabilities of my generation code. So in all of the red statements, this person became the friend of somebody in order to get information, and he did it a lot. So like essentially this guy was kind of a cool spy or villain and like could have been an interesting character to write more interesting things about, but my code didn't. So I come from data visualization as well. So like this is a UMAP layout of just looking at race, gender, age, and social links. And what I could have done at a sort of meta level is look at the outliers in this and try to understand the groups and like tell a bigger picture story about this world. Like for instance, this is childless male dwarves shoot up in battle up there. Maybe they would have made an interesting story on their own. Maybe the battle places are all the same or whatever. So, so essentially, both of these projects were not weird enough, I think. They just aren't interesting enough. And there's no interactivity. So for NaNoGenMo, it's just like generate this 50,000 words, right? NaNoGenMo is National Novel Generation Month in November, where lots of clever people sort of under the radar do interesting things. But anyway, there are very few glitches in these two projects, and so they're not super interesting. So in the last few months, I've been like thinking about what's fun because of a bunch of things, but fun, Marc LeBlanc, the game designer, has these famous definitions of types of fun, right? The ones I'm interested in are make-believe, narrative. I'm less interested in challenge, like shooting games, discovery, self-discovery, and expression. Those are kind of the things that I think I'm interested in terms of making things to support. These are just a couple of other things on the game generation front. This is just things from NaNoGenMo. This is a novel generated by playing Ski Free by this woman who basically goes through this whole long blog history of how she instruments this old game and gets it to output text for the stats that are being displayed on the screen. And it's a little bit like my dwarf thing, but it's a lot more interesting. I mean, she's probably like just doing better writing. It's a really entertaining project. And then this one is a lot like the Dwarf Fortress thing I did. This is annotating a Mario playthrough with just descriptions of what's happening, which I have to admit I love. I want to do this with Minecraft. It's been on my to-do list for a long time to sort of narrate things in Minecraft. But I like that project. Okay, so looking at some other things, start thinking about story generally before we get to slightly more interactive things. So Ralph Koster in The Theory of Fun for Game Design says, can stories be fun in the way games can? Well, maybe. This is a fantastic project, speaking of NaNoGenMo. I love this to death. This is Kevin Davis took Moby Dick and turned it into a game. And it's essentially, I'm so jealous that I didn't think of doing this. But essentially it's, he parses it in various clever ways and then comes out with these like twine-like choose your own adventure links for things like, so this is sleeping with Queequeg and to try to move his arm, unlock his bridegroom clasp, turn to page 57. To see the opening maw of hell with endless pains and sorrows there, turn to page 66. This is just hilarious. So here's another section. So things about Queequeg. To know not the desolation that broods in bosoms like these, turn to page 38. I mean, it's a weird way to read it when you flip around through the links, but it's a good remix. Like if you know the book, which I don't actually, but it would be a fantastic way to experience it if you knew the book. By the way, this guy, Kevin Davis, is the guy who turned Wikipedia into a text adventure game. He's essentially an unheralded genius, I think. And so Raj's work. So I really loved this paper and tried to reproduce this while I was doing like an Innovation Week thing at Google Arts and Culture. And it's really, really hard. Maybe Raj and I can talk about this someday, but trying to do the open entity extraction on a new text and turn it into a good knowledge base and then turn it into a game is super difficult. And I produced horrible, horrible fairy tales doing this. But it was definitely an inspirational paper. The thing I did last year for NaNoGenMo, I don't have an interface or anything to show you. I've written all the backend code, but basically I want to allow people to regender Pride and Prejudice. This is essentially a fan rewrite, but it involves a shitload of NLP. I labeled the entire book. It was because the co-reference models for an AFRA are terrible when it comes to literary text like this. But essentially, like you can set up whatever relationships you want by allowing the pronouns to be changed wherever you want. So interestingly, if you just swap a bunch of the key pronouns to the opposite binary gender, you get this first sentence: a single woman in possession of good fortune must be in want of a husband. Now, reading this as is doesn't give you a sense of what that means about the world, because that could be true even in Jane Austen's England of the time. But then when you read a more bisexual matriarchal universe paragraph, you see it very differently. So Miss Darcy danced only once with Mrs. Hurst and once with Miss Bingley, declined being introduced to any other lady, and spent the rest of the evening in walking about the room. She was the proudest, most disagreeable woman in the world, and everybody hoped that she would never come there again. And so Mr. and Mrs. Bennet, their roles are swapped. Mr. Bennet is very angry because Miss Darcy slighted one of his sons, because he now has 5 sons. It's actually super interesting reading this. It's a shit ton of work to get all the co-reference relations labeled right. I'm not saying I made art. I'm saying I made a thing that helps make the familiar strange in a way that it should. Like, I think that that's actually interesting. This is actually from an article about using GPT-3, a GPT-3 tool to write a novel. So I think that's a cool use of NLP. Now I'm going to talk more a little bit about, say, poetry and game playing with images, which is something that's been obsessing me recently. I've done a version of this project several times, where I take a source image and do some kind of processing on it, and then essentially generate poetry from it. I'm not the only one who has done this, but I keep returning to this in various ways, because it shows various weaknesses and strengths of various different models that are out there. So Midjourney is a place I've been hanging out recently. It's a text-to-image diffusion model generator that's very fast. So it's very, very fun to play with, as I'm going to talk about more later, because it's fast. By the way, they're in open beta, so this is not like a you can't get in situation. So there's 2 images I made, and I put them through this process. I don't know how well this is going to show up, but essentially this is like a binarized grayscale version of the first one, where the image API said it's a natural landscape, it's a land lot. And then my poem archive is just matching words. It's not super smart. This isn't generated poetry. Found lines that match some of the other words in the return description, and they're sort of randomly placed here. So sometimes they're easy to read, sometimes hard. This one, the banana, is just funny to me. I smiled upon the other hand and said, "Spirit of smiles and tears, you came to me in the night. Fruit, banana family." There's something great to me about the juxtaposition of these labels that are very like generic and sort of dumb and unemotional with this old-fashioned poetry. So here's another one: atmospheric phenomenon, rainbow. And then we have poetry about rainbows. And this is actually an image of like an asteroid striking something, which, I mean, it doesn't matter. It looks like a rainbow type image, right? And then this is like a picture of a lawn chair in front of a church. And so the words that came back, because they're randomly displayed, you can't really see the yellow one that says cloud. But the way the poetry is laid out here, you end up with the last line being, "The atmosphere is not a perfume and has no taste of the nature," which I find funny. So I find these weirdly fun. I think because it's relatively quick to make them, I'm just using local Python and an API call that's fast. And I find like the juxtapositions and the reductionism funny. I think they're funny. So I guess it's the funny because it's true kind of funny. So this is some other people who've done this. This was a research project I liked a few years ago. This was Best Paper of ACM 2018. They did something similar, except they actually trained a GPT-2 model with poetry and output these poems. I tried to run it a couple months ago, and I can't get it to run. This is just super classic. This is not like Flash is dead and now the old games went wrong. This is a couple of years ago. This old project like is unrunnable now. Like the work it would take. I mean, essentially, I'd have to like take their data and reproduce it with new frameworks. This happens so often with any AI generated creativity code. And so here's another thing. I'm not going to do this in any detail, but I'm just going to say like making toys out of poems is also sort of fun. I did this in more detail in previous talks, but I took Word2Vec models and I basically presented a very laboriously created React interface with like nouns and other words that were in the Word2Vec model highlighted with sort of a color scheme to show how close the nearest words in the model were. And then you could click on those words and edit the poem. So it's essentially a remix using Word2Vec models. So this is the original Basho cute haiku. And here's an edit, the last wet shower. Even the basil seems to try a little cap of dirt, which is very cute. But then if you throw in a different Word2Vec model, this is Nerd2Vec, which is like science fiction and Star Trek scripts. You can do things like the last hot meteor, even the lizard seems to need a little robe of guts, which I think is great. So this is genuinely fun. So I mentioned the UK Pavilion thing. So I worked on this for Kyle McDonald a couple of years ago, and then COVID hit and they delayed the expo in Dubai. This is essentially an effort. The UK government wanted to basically have this poem where people would put in a word and then you'd get a couplet, 2 lines of text coming out. The pavilion was designed by set designer S. Devlin. It's a little hard to read the couplets on this display. There was an online version somewhere too, although I haven't seen that one. So I worked on training the model and the reviews with poets, etc. But the way it worked was essentially this. You would give the GPT-2 model a context of good poetry, like the style they were after. And the previous few lines of generated text, a user would input a word like snow or whatever, like a topic. And then we'd get a couplet, 2 lines containing it. It could be in either line, the way we trained the model. And we update the context prop to contain those lines. So you essentially get kind of a telephone game where it just, each time it's generating, it knows what was generated before it. So this is like a sample of the output. So if this was using random words to just test it out millions of times, but move, if that was input, the lines might be, view me, my eyes on this cold wall, you will never move out of this picture. So that's the couplet where it shows up in the second one. And then the next line generated using that as context is, without a third leg, and I promise you, you'll always step out of this picture, your one-year detail. We're talking about music, but you know, when you do, you might find an item in the road that brings the whole picture of truth, the last shade of the paint in a window's shade. You'll know, but how can I tell you? How can I relate? The light that flickers in a mirror, the shadow of a hand. So, you know, I mean, it kind of sounds like modern poetry. It doesn't like, you get accidental, fun conjunctions that feel poetic. It's the classic generated poetry thing, but it's not bad. So this whole telephone game thing where the output of a model becomes the input to a model and then back and forth, I like that. I think that's fun in some weird way, often because of the distortions that it produces. So this is something I've been working on and off for a couple of years that I haven't built a good interface for yet. I have a really crappy tool for myself, but I wanted to sort of show what's interesting about it. One of my inspirations was this. Caroline Bergvall is a performance poet and artist, and she did this thing a few years ago. Now it was hard to find a copy of it, where she just collected 48 different translations of the opening of the Divine Comedy. And they're all like slightly different, even though they're all translated into English. So I find that wow, I said 47 here, it's 48 over there. Anyway, they're interestingly different, even though it's all translated into English. I think this was an interesting data poem. So I was interested in this, but I'm also just interested in just like translation between languages. When I was in grad school, actually it was undergrad days, one of my professors used to tell this anecdote: the spirit is willing, but the flesh is weak. Translated into Russian came out as the steak is good, but the vodka is not so great. This is the usual problem where like the sense of these sort of well-known phrases isn't carried across, and they become very literal. I don't know if this is a true case that happened or just a story that he liked to tell. It was Norbert Hornstein. Anyway, so I made a thing that simulates balls who are agents running into each other. This is in P5.js, I think. And the ball that's black is an English speaker who comes in with a message that she has to deliver. And these other balls are speakers of other languages, and they run into each other and they pass on the message in their language. And at each point, it's translated into the recipient's language and then translated again into the next recipient's language. So you get a case like English speaker says hi, the French person hears and translates it to salut, the Korean speaker gets it translated. And then in order to interpret, I translate everybody's line back into English to see, like, in English, what are they saying now? And using the current Google translation algorithm, there's like this many languages, there's quite a few. But, and what you can see there on the bottom is like an example of my output. So the 203rd strike is language MS to Italian, and that's the Italian translation. It was Miss Scarlett in the library with a pipe. But in reality, there are some pairs that apparently can't translate between. So this one here, L is Greek going to Aymara, which is a language of the Bolivian Andes. There you get an error when you try to translate between them, which I found interesting. So I've put in lots of phrases, and this is one that was just an interesting output. So E.E. Cummings, listen, there's a hell of a good universe next door, let's go. A thing I think about a lot. And this just is very, very rich. Like this was one random transcript with a section of it. So English to Kurdish language, listen, there is a good universe beside her, let's go. So of course, there's going to be gender going on in a lot of languages that doesn't end up translated right. English to Albanian, listen, there is a good universe nearby, go. So it becomes a directive, not let's go. Kurdish to Finnish, there's a damn good universe, gone, some kind of tense problem. Belarusian to German, or Belarusian, I don't know how you actually pronounce it. Listen, next door is a very good corner, so let's go. Then we get, listen, the side door is a very good angle, let's go. Listen, there's a damn good universe, go. Please try listening. This is Japanese. Japanese is polite. Please try listening. There is a very good universe around. Go. That's not so polite. Japanese to Kurdish. Please try to listen. There is a very nice corner on the side. Okay, let's go, etc. So what's interesting here is you can see when you read it, like, and you start looking at the pairs, universe has become corner in a bunch of languages, and corner becomes angle in a bunch of languages, and next door becomes side door or neighbor. And then of course, let's go becomes go, the directive, instead of let's go. So I find that surprisingly interesting. Then there's this whole section here in this particular transcript where it turns into visiting scientists. And this is extremely difficult to follow. It seems like something in Somali is going wrong. But like there's this thing in the middle. Listen, next to it is the hell of a talented scientist. All right, let's go. And it's just really weird, this whole scholar thing. And then the final line after 374 collisions, listen, next door is a good cosmic hell. All right, let's go, which I can kind of get behind a lot of times. So this is just really funny. Like doing it is funny. It needs the things that are fun in it are that it's both the random elements of the intersections and the random languages. And then in looking back at the transcript to see how it happened. So I can see tons of great interface ideas for this, or games where you have to try to get a message across or get the most bizarre result back or whatever. Just as a model for something fun, there's definitely something here. Too bad my current JavaScript skills are so bad. And just, you know, this is obviously less fun, but network effects are big. We all remember the World of Warcraft corrupted blood pandemic, and if we don't, you know, epidemiologists learned from how people behaved during this contagion in the world. These kind of viral passing messages situations are really rich in a lot of ways. Maybe the example I just showed is less rich in that it's just about what pairs of languages do badly in Google's translation model, but that's interesting. And there's clearly a whole bunch of reinforcement learning on multi-agent GIM environments and just simulations of multi-agent environments. I'm really interested in gossip passing. I need to be unemployed for a while to actually investigate these things, but they seem like a fun place to try this out. So different telephone game. So I've been playing around in this text to image generation community Midjourney, and some of us actually started a telephone game. Actually, Sarah Northway, who's a game designer, started a channel that's a telephone game. And this is essentially, if you think of Midjourney as a toy where you play with generating images, this is a bunch of people who made a social game out of the toy. So this is going to look like word salad because it is. So Sarah says, after a thread of messages, yesteryear's miming goons, oh vertigo awaits, bring ghastly tragic lore. And Ancient Chaos, who's playing the game, says, yes, terrors mining guns. So he's doing a very much sound-based telephone thing here. Yesteryear becomes yes, terriers. Miming goons becomes mining guns over T-Go. So essentially this is in no way a sensible instruction to a machine to generate an image. And so that's why this is sort of a funny game. So we got this terrier with some kind of a still, which is adorable. I love this picture. This is the kind of fun, surprise, bizarre happenstance thing. It's definitely an interesting game. So this guy, Daffy, did this one. Felon ranged through Guernsey Din, Theocrat surfaced Limey Scion. And I'm actually playing by different rules. They know this. I'm basically like chaotic good and they're chaotic evil for me. Like I'm constantly trying to make English sentences or things that are not word salad, but also taking into account the things that they have said. So I tried to turn this into a criminal forest ranger in Jersey, didn't believe God was an English lord, and like see what it could come out with. And it came out with some things that were not terrible. You can see how it's getting forest into these, English lord. It's trying really hard. One of them is like some kind of priest. It's always fascinating trying to balance what they're doing, what I'm interested in, and then what the machine is going to come out with. And we end up having a lot of discussions of the word salad results, like kind of interrogating what the model is doing. So this one is Ancient Chaos said, has Laverne tended bars, shame Dallas, aground, a gust showdown, snoring. I mean, total word salad, who knows what it's going to come up with? Well, it came up with a ship, and you know, Daffy is like, it's because of aground. Like it didn't know what to do. Like it doesn't have this as any kind of related caption in its data set, except for the word aground. And I think, you know, one of the things that makes it fun is seeing what it comes out with when you give it something completely nonsensical. So speaking of nonsensical, Jenny Polodna is a game designer that I hang out with, and she did this was in my newsletter too. I invited her on the beta, and she's very funny. She writes comedy games. And she did this, a centaur, except the man part is a jumbo shrimp. And she's like, it fucking nails it, first crack out of the gate. And she posts this, and I want to say 57,500, 57,000 likes. Like, it's just 57.5K likes. Yeah, so that's a lot, isn't it? Anyway, it's like, this is ridiculous. This was everywhere. This was on Reddit. People were saying, oh, did you see the shrimp thing? Like, I mean, it was just ridiculous. Anyway, she's having a good time with it. There's another thing in the theory of games world, like classifying, collating, exercising power over the contents of a space. I mean, this is that exploration thing, the like, what will it do? What can it do? How and why? And trying to understand the model is absolutely fun. And Midjourney is so reactive that it's easy to do these things quickly. So last night there was an office hours voice chat on Midjourney, and David Holtz, the founder, brought up the thing that, like, we've seen a lot of people use it as sort of art therapy. The example he brought up was someone typing in a dog in heaven and finding out that this person's dog had just died. So I tried a black and white cat in heaven. My cat died in February, and got this rather evocative picture. I think that, you know, there's, aside from just being fun, there's this kind of self-expression. People who aren't visually talented, like I'm not, obviously you can see from my slides, being able to make things with a sentence that are artistic is actually a profound thing. And another thing David said is that I think is true, and I've taken this opportunity in front of an academic audience to say, most AI research isn't about watching people use the tools and trying to build real things and feel engaged and joyful with them. And he feels strongly that we should be doing that. And I've learned a lot watching people play with it and playing with it myself, and trying to understand, like, when it's fast and reactive and not like a slow job that you have to wait on, what is different about it. And yeah, obviously I know about Kai and WIST and all of the workshops happening on interfaces for AI, but there's still like not a lot of stuff that you can really play with that's fast. I did another sort of telephone game that was less interesting to me than the things on Midjourney. So this requires an API. Midjourney does not have an API, and so it's all just, you go on there and you type. So Disco Diffusion is a model that runs in a collab, and you can code around it. So this was a thing where I was interested in two models talking to each other, a captioning model and the generation model. So you start with a prompt like a lonely traveler walked by a lake, generate with Disco Diffusion, caption it using a good caption model, and then you generate a new image from the caption and see what happens, like what's the drift. Gina AI is an interesting AI company. They wrote a wrapper for Disco Diffusion. You can just do import Disco art, and you can run it from a single command. It's very easy. And Antarctic Captions is a good, fun captioning model. Sorry for the colors. So Disco Diffusion, I only ran it for 200 iterations. It still takes like all night to do these things. But I'm not going to bother you with the details, but you can see that in the upper left, I've got a castle, and in the lower right, I have some kind of fire truck in a field. So this is the drift over captioning errors and the image. In particular, we started with a castle on a hill above a green valley, stormy clouds, that's on the left. And then the next one, the caption that it came up, the first caption was a green castle standing among rolling green hills on a white slope down an incline. Use that caption from the first image to generate the second image, etc. So it ends with this sequence of fire truck related things. And when I looked closer, it turns out that there's actually a data glitch that I think caused this. So Antarctic Captions came out with a castle sitting on a grassy field topped by trees next to a wooden fire not hydrant. And so essentially the model didn't know what to do with hide, and it generated next to wooden fire. And so then we get all of the fire trucks. So for me, this feels a little bit like you're looking at a bunch of hills in the mist receding in the distance, and it's not so clear what's furthest in the distance in these games. Here's one with a woman looks out the window of a fairy tale castle, and then you can see like there's a bunch of window stuff on the top row. We get into green castles for some reason, then we get into blue castles floating on clouds for some reason. All these are in a GitHub repo if you want to look at them in detail. This is one where I was like, okay, I'm not actually having fun yet. Like partly the images aren't very good, etc. But if I add in GPT-3 and try to make it a little more story-like, well, it just gets even more randomly bizarre. You can see in my repo what's going on here, but we start from a castle where there's a woman with a witch, and in the lower right corner, we have some wizard flying a kite. I don't know if we're having fun. So the captioning is glitchy, maybe in a fun way, but it definitely with some errors. Some of the image generation models are less good at reproducing the caption, so there's drift. Making this real time would improve it. We need an API for a good model. Disco diffusion is okay. You have to run it for a long time to get a good picture, and it takes a long time. So I tried DALL-E 2 today because I only just got access, but they don't have an API yet. You have to cut and paste, and I have to cut and paste between Antarctic captions and DALL-E. So this is a case where I basically gave a prompt. The woman looks out the window of Fairy Tale Castle. You get the picture on the bottom. Antarctic caption says a woman looking out from a window at a castle, which is a fine thing. And then we take that prompt and we do another generation in DALL-E, which is the picture on the bottom. The caption model says a woman standing in front of a rectangular window with a view at the front of Anne. Okay, so there's another caption glitch entered in here. So say if this was an interactive app, we take the second line. A man looks out a window outside through the curtains of a door of a castle, which is just a bizarre word salad. We get that picture. And then we get these different other descriptions, which are slightly different. We're actually having more fun, believe it or not, I think, because the pictures are better. The captioning can be more accurate, except for the weird glitches. I did have to tell somebody to fix a PyTorch version bug that was introduced overnight in a fix. This is classic with all of these code projects that use AI. So I think this could be a fun app. I'm conscious of our time. I'm going to go kind of quickly through this to get to sort of a point. DALL-E 2 has some interesting things. The in-painting and out-painting really interest me. I haven't played with them yet. This is a good example. I'm not going to play it because of time. Nicholas Rugo did a giant isometric town in DALL-E 2 and has a tweet thread on how he did it. And the tweet thread's really interesting. I want to replicate it, but making castles, obviously. And what's interesting is when you zoom in on the giant file, you find these weird disfluencies, things that don't quite make sense, which figures. I mean, it's an AI generated model. I'm afraid to zoom in on these pictures, I'm telling you. So you probably all know about like the bugs and glitches in Red Dead Redemption 2. The Grannies video about the people who investigated these is a fantastic video. There's an article that links to it, and I got access to it. It's only a 17-minute film from the creator. This is essentially the big open world thing where a bunch of people had played the game and gone through the story and then turned the world into a toy. They explored it, they found glitches, they investigated the glitches, and then sadly the company fixed them. Microsoft Flight Simulator had some of the same things. This, again, for time, I'm not going to play it, but this was fantastic. This one was like, on the left is an example of essentially a bridge that was displayed wrong and has cars flying up and down it. And of course, the first thing the guy does is try to land on the top of the thing, just like people try to land on the skyscrapers that shouldn't be there. This is a case of playing a different game within the game and turning it into a toy. And then Dwarf Fortress. I mean, we all love Dwarf Fortress. The bugs are some of the best thing in it. I mean, I just think, like, are they bugs? Are they features? Are they just emergent behavior that, you know, like, I mean, never-ending festivals, that's just a fact. It's not a bug, right? So I've been illustrating some of these in Midjourney and getting results like these. I posted this yesterday. Unconscious companion vanishes deep underground after waiting an hour. Fantastic images. Like, I didn't say style or anything, just those. Whereas when I throw them into DALL-E 2, I get people lost in the underground in London, which they just have a different model of the universe. I know which one I'd rather be in. So to sort of wrap up, I want to talk a little bit about that issue. So Jay Rosenbaum did this dissertation about looking at transgender non-binary people in these models, essentially, like starting early. And attention gain in 2017, when he put in phrases like a man at the beach, a woman at the beach, a non-binary person at the beach, we get an empty beach, which is really poignant, right? So now in Midjourney, we get some people on the beach, and in DALL-E 2, we get some people on the beach. They both have stereotypes. This is in a Twitter thread you can read from yesterday. They both have various stereotypes associated with them, but there's content. These models are better and more inclusive. We need to do more work on things that will support things like poetry generation, story generation, emotional output. There's a couple of links here to some useful corpora. Now, training models to use them is a giant shitload of time and effort and money. And then we should also be noting that people have biases, and so do the models and data sets, and more so the data sets built on people's uses of these models. Do you recognize there's a telephone game going on? So for instance, the Simulacra aesthetic captions readme notes that one user really likes using the model to draw a world tree or the earth represented as a giant tree. And so that's in the data set a lot and rated by people a lot. So this will have an impact on art produced from this kind of model. Georges Perec has a lovely book, An Attempt at Exhausting a Place in Paris, where he just sits there and is a labeler, annotating what's happening around him. And then he starts commenting on his own annotation behavior. Like, why are two nuns more interesting than two other passersby? Probably because they're unusual, right? A little girl flanked by her parents or by her kidnappers is weeping. That's him adding a filter on what he sees there because he doesn't know what he's seeing. And then in one of his observations, I don't see what takes place a few meters from me. I don't notice, for example, that cars are parking. The limits of annotation. However, we do have some artists who are starting to release their own models, their own data sets, and their own how-tos. So this is Caliuga releasing Pixel Art Diffusion, which is a pixel art generator specifically for pixel art. And she has a collab, and she also released a how-to, like how to train your own model, which is a fantastic thing. So I think, you know, when thinking about things we can make from these things and from these data sets, we need to have a big vocabulary. We need to have lots of kinds of models with lots of things in them and lots of different models, like maybe a pixel art model. And ideally, we share these things. Some academic research, like there's people who did a game tool recently for generating games. It turned out that they couldn't share the model they had trained on OpenAI. It was a tuned GPT-3 model, and they couldn't figure out how to share it. So, okay. I'm basically a minute over. Thank you so much to the people who are publishing collabs for cool applications and their art tools, not just stats on state of the art. The academics who actually help out people like me. So David Memon was hugely helpful with tooling for labeling gender co-reference errors in Pride and Prejudice. He has a book NLP project that's great. Companies like Midjourney that are actually making things for people to use and want to have a community around them, and the friends there who let me share stuff are great. And the people who are making open source and sharing and publishing how-tos and sharing their data sets, I love you. you make it fun to tinker. And so here's a lot of info. Raj mentioned my newsletter. It's true. If you like this talk, you probably would like my newsletter, although there was more of my own stuff in this than usual in the newsletter. Arnicus.substack.com. I'm Arnicus on Twitter. And I have Medium articles that talk about some of these projects in more detail. And the links are there. I'm going to spruce up the links and maybe write this up a bit more. So there you are. I'm sorry for going over. How do I stop sharing?
All right, thank you, Lynn. That was a fantastic talk. I particularly like all of the non-standard, let's not focus on soda numbers, but what can we actually do with these? Okay, so we're going to take a couple minutes to do questions. So if there's people here who have questions, you can come up and ask, or like write them in chat and I can see them for the people that are remote. So while people are writing through those,
yeah, Mark Alexander posted my out-of-date website, but sure, you can find links to my stuff there. Thank you.
Sorry about that.
No, it's fine. Thank you.
I do have like one, I guess, softball question. Like, have you played a bit with the AI Dungeon, and what's your thought on that?
Yeah, so I've been going through a lot of the text writing tool aids. I've definitely played with AI Dungeon in various versions, and I've been playing with like just creative writing tools. Pseudo Write is really fun, by the way. I couldn't squeeze it in the talk easily, but I love their interface and models. Yeah, AI Dungeon. So I mean, frankly, a lot of GPT-3 generated text is not good text. So I have been less interested in it without being solidly on the rails with sort of very heavy prompt context. It's good at lists. I'm less impressed by it out of the box than I would be. I can't wait to fine tune and try some more different things, especially now that we have Bloom available.
yeah, I wonder if it would be very interesting, like some of the things that you've done of take the AI Dungeon and run it through Midjourney, perhaps, to potentially get like visual output pairs for the actual text.
Well, they got Pixray, Tom White's Pixray app hooked up to AI Dungeon in some form. There was some weird politics around that and licensing issues, but they definitely were looking at that. I mean, tons and tons of game people are on Midjourney, like you would not believe how many. It's so clear from the concept art and the game prompts, and yeah. Yeah,
half of my Twitter feed is just AI generated art at this point. Yeah.
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 I had to make a separate list.
Yeah, we've got an in-person question here.
Oh wow.
Cool. Thank you for the talk. Unfortunately, I missed the first half. I missed the first half of it, so maybe you talked about this there already. But did you discover like any hidden language with DALL-E or Midjourney as a bug? And have you played around with that?
So the hidden language thing was kind of debunked a lot in many Twitter threads, from what the definition of language is, from Stella Rose Biderman to various other people looking at that. With Midjourney, I don't know about a hidden language. I think they would laugh. If any of my friends there are watching, they would laugh at that. No, but just the word salad we produce in the telephone game, or that the others produce. I'm resolutely sticking to English sentences.
Okay. Yeah. Well, no. I actually just saw somebody published something called a prompt book for DALL-E on how to actually tailor your prompts to DALL-E so as to get basically better generation. So all the little trending on ArtStation or something like substring. And it was hilarious because like that actually made it out of AI Twitter, that made it to like D&D Twitter, and everyone's like, oh, this is basically just a book of spell incantations at this point.
Yeah, I think a lot of us have thought that they look like incantations and spells. Absolutely. Somebody actually came on Midjourney in the chat early on and said, are people using it for divination? And like, there was a serious discussion about that, which like, why not? I mean, there's a bunch of randomness going on in there. Why not? People are definitely using it for art therapy.
Absolutely. Okay, cool. I think let's wrap it up there. So this is the ACL mandated 30-minute break for all the workshops. So you guys can go outside and get refreshments. We'll be back in 30 minutes with Tim Rick-Tashel talking about knowledge-intensive reinforcement learning.
Thanks, Raj.
All right, then. Thank you. I'll
Thank
see
you,
you.
Lynn.
Yes.
I don't know how to use this app.
Do you want to introduce him? Like our voice is dying. Peter Jensen found there was somebody like making this t-shirt. Yeah. I'm like, he's like, who got the t-shirt? I'm like, Peter's gonna be like credited for this t-shirt.
I'm gonna wear mine tomorrow. It's custom made or it's sold.
It's custom. It's like SD. Yeah, it's like, yes. Of course, I have to have this shirt.
Yeah, that's a perfect shirt for you, right?
It is. I wrote an entire dissertation on this.
I lost my tag in like the first 1 minute that they gave it to us.
I've lost it. Oh, I should know.
Yeah, sure, I can introduce.
Okay, good. I will.
But you be here.
I will be here.
Yeah, like those fun. Oh yeah. The conference.
He's
quite nearby from your. All right.
Yeah.
You.
I live there, so I'm my house is like 10-15 minutes. Yeah.
But yeah, it's only
She was missing about Microsoft Flight Simulator. And they basically are just
period of skipping a couple and that's happened.
oh, it's in the thing.
Good go.
Apparently,
Years.
so there's like a couple of startups. It's like a very interesting application. Because like using live session as a way to basically it's like how people so instead of like creating a pool in chat.
I bought a funny little
Try to
guide to re-entering society
It's
that
very interesting. It was
silly jokes like
these guys out of like
would answer, but frequently asked questions like how many batteries should I bring to my house when I was at a dinner party? It's like totally nonsense.
basic. I think they were partnering with real.
Okay.
So, like,
They are waiting with its console. Then try to run to how to use control. Okay. See finally adversarially.
Yeah. I think that's like a really
Yeah.
because like the more I run more on the more I realize like, you're just really basically like situation of the game. It'll do
what the specification is, but like not really in the way that you do it. It's too visual. And the more time I spend doing like all the things like text generation and whatnot, like
one of the few actually useful people with that.
yeah. No, it's good because like you take something that's perceived and then you turn that. It's like,
yeah, finding errors and that's under the other like the algorithm or and like yeah.
yeah.
Oh, Microsoft has game. Game trouble.
Yeah, they do. They have Xbox.
You can do the research.
There you go. When I interned at MSR, people from Xbox that's what I did, PCs in a game. And like it was kind of well, also this was like pre-transformer era. Oh, that's kind of and so they were what they ended up doing was it was this pirate character. Pirate's parent. Like and like that actually makes a lot of sense. Yeah. And then they were looking at like engagements and things like that. And it turns out that a lot more people were talking to this parent who was supposed to be just like just a side character for flavor than the actual like main characters. It was just like because it was like so random, it was generating like a lot more popularity, like on forums and like everything. I was just that's crazy stuff.
So you don't really have any chance to engage with other Microsoft, Minecraft.
Yeah, so
it
it is very big. Yeah. I'm not Microsoft or anything. I'm AIG right now. It's like it's kind of nice because I some happy stuff. Like I was asking this he's on the Turing team at like scaling team. I was like, oh, that's what him and some of his like colleagues like, what are you working on? And like half the things that yeah. All the secrets of like, I guess how big is your US language?
That's unfortunate that when especially when you do the what are you working on? So and that's it. Like, they just have to stop over this.
And we have the kind of best LN one. But there are some teams that like I am actually
Oh, really?
education. So like Lynn sort of very briefly mentioned it, but I had a previous work which was looking at turning story.
Are they based in Europe or?
No, they're here. Well, at part of the team is here. So it was Mojang. They got it right. So the education team is fully here, and then there's like the actual Minecraft is like basically the education version is simply stripping a lot of stuff out in order to get more level from like students on like tiny laptop. But the whole idea is like help. Teachers basically try to make the lessons steps that takes a very long time. But they have enough evidence that they do like improve learning for students.
You have to make
What? They can't hear us. The only place they can hear us through is through that mic, or if I
Mic on. Is this mic on? No, this mic is on.
Actually see it. Oh, okay, maybe there's plenty of places here. Pretty good. Try this in December. Sunsets. Yeah, it's good. Is there a way to pick up the laptop, or should I just pop up? So Alien. And so all on standby, and they just dump everything for the first 3 days. And 4 days, I had to drive straight north to Vancouver, and then to drive north from here. And so the process, that's true. Yeah, academic art.
Great things. Something that somebody has almost exactly the same ability. And so for those How are you doing?
Try to cutting edge AI technology, to solve. So I figured out all the steps had this come up with the most efficient solution. It did not work.
Maybe you want to get a 50.
I went to Cardinal. No, I didn't. Maybe it just got this. Can't remember. Yeah, I was thinking about it. So it's been offered on since I have an actual job.
Yeah.
Yeah, I know. It was also simple. Spread. Have prototype steps for simulated.
Hi everyone, it's a great pleasure to be here at the workshop. My name is
Right.
I hate Edge.
Yeah. I feel like the technology is really
Better.
Hi everyone, it's a great pleasure to be here.
Okay. How do I share? So he's going to be here for the live QA. So I think we just say, since he's not, well, I'm going to play the video, but he's actually here for live QA talk. And just introduce him. Start by.
So hello all. So the next talk is by Tim Proctorshell, who is a researcher at DeepMind and an associate professor at University College London. His work focuses on reinforcement learning and open-endedness. And today we are going to play a video by him, but he's still going to be there for QA at the end of the session. And he's going to be talking about knowledge-intensive reinforcement learning. And one of his works that I really like recently was NetHack Learning Environment, which is a really open-ended reinforcement learning environment. And if you have agents which are doing amazing on environments like text-based games or anything, try to see them fail on NetHack Learning Environment. So with that, I'll just play the video.
reinforcement. I'll first cover what I see as current limitations of reinforcement before talking a bit about two environments for open learning, namely NAACL and NAACL, that have been released in the last 2 years. And then at the end of the talk, I'll present a recent work from Jesse New.
We don't hear very well in the Zoom call.
So let's start with the limitations of current reinforcement environments. I'm pretty sure that everybody's familiar with the framework of reinforcement learning, but just as a quick recap, generally speaking, we have an agent and an environment, and we assume that that agent can perform actions.
That's better.
We get back a observation and a reward, and based on that reward and observation, we'll choose the next action. And the task that that agent has is to maximize the cumulative reward over time by acting in this environment. And this has been tremendously successful over the past decade. We've seen reinforcement learning used to play superhuman in games like Atari, StarCraft, Dota 2, and also the board game of Go. So this is really fantastic. And at that point, you might, ask, okay, what's left to do? Alexander wept for there were no more worlds to conquer. But actually, if you look a bit more closely into some of these environments where reinforcement has been working really well, at least reinforcement tabula rasa from scratch, basically without even demonstrations, then these environments generally have very tiny action spaces. They're what's called singleton environments, where every time you play the game, you see the same kind of environment configuration. You're not going to be getting surprised by any kind of novel observations. And the environment itself is a deterministic environment. So that means, for example, even for the hardest exploration problems in Atari in this pocket learning environment benchmark, namely this game Montezuma's Revenge, you could memorize over time the sequences of actions that lead to certain states from which you want to explore. And you can, when you reset the environment right, you can again just execute the same sequence of actions that will allow your agent to arrive at the same state as before. And that makes things very easy. Not very easy, but it makes them considerably more easy when it comes to exploring. So
the people online are having audio issues, so we're gonna try to learn the
and that makes things very easy. Not and so on is very nice, but eventually we want to have a in the real world. And reality is an extremely variable environment, much more noisier and more dynamic and more variable than a Go board or an Atari game. So that doesn't mean we have to stop doing research in simulated environments, but we need to
Does anyone have
to drop some of the assumptions of the algorithms that we've been developing. We need to do something different to make progress. We must close the gap with the real world by progressively removing simplifying assumptions. For example, environments might require external knowledge to be solved. I'll give you an example of such an environment in a bit. Environments might involve natural language that you have to deal with. Environments might have photorealistic observation spaces or makes things very easy. Not very easy, but it makes them considerably more easy when it comes to exploring an environment. So what I would argue is that eventually, right, we want our agents to step outside of the simulation. We want our reinforcement learning agents to do practical things in the real world. So solving StarCraft 1, 2, solving chess and Go and Atari and so on is very nice, but eventually we want to have agents that serve us in the real world. And reality is an extremely noisy, dynamic, variable environment, much more noisier and more dynamic and more variable than a Go board or an Atari game. So that doesn't mean we have to stop doing research in simulated environments, but we need to drop some of the assumptions of the algorithms that we've been developing. We need to do something different to make progress. We must close the gap with the real world by progressively removing simplifying assumptions. For example, environments might require external knowledge to be solved. I'll give you an example of such an environment in a bit. Environments might involve natural language that you have to deal with. Environments might have photorealistic observation spaces or might have a constant stream of novel observations. So you can't really memorize sequences of actions that let you arrive at certain states. You have to really adapt dynamically to this constant novel stream of observations. The task or dynamics of the environment might change over time, and there might be a large or even unbounded and dynamically changing action space. The environments might not have any reward, or when they have a reward function, that reward function might be very sparse or very noisy. And I guess there are even lots of other problems as well that I haven't even thought about here. So what happens when we start dropping these assumptions one by one? I think at that point we start to look into very exciting, much richer and much more complicated, difficult environments for reinforcement learning research. One example of an environment that's, I think, much more exciting than the ones that we've been using over the last decade is Minecraft. And rightfully, Minecraft has started to see a lot of interest in the research community with multiple competitions at major AI conferences. So now we start to look into more open-ended problems, more open-ended domains to do RL. And at that point, we also need maybe more open-ended solutions. So what's open-ended learning? Well, basically at that point, we want to have reinforcement learning approaches or learning approaches that are adaptive, that over time start to discover the stepping stones of intelligence. That could mean, for example, to co-evolve both the environments or problems as well as the agents that are learning in these environments. It could mean to have auto-curriculum learning methods that in a self-supervised way basically teach an agent what kind of problems to tackle at which point in the learning progress in order to start from problems that are easy or doable for an agent to then gradually increase in complexity and difficulty. It could mean teacher-student learning processes or population-based training or evolutionary methods. It could mean to have agents that are intrinsically motivated to strive for discovery in an environment. Is this practically relevant? Well, at this point, I would argue, actually, we already know that open-ended learning works. It's an important ingredient of lots of the recent RL breakthroughs that you've been seeing in the press. So, for example, self-play as an AlphaGo can be seen as an open-ended learning process. Population-based training as an AlphaStar and Excellent is an open-ended learning process. Intrinsic reward mechanisms like random network distillation, RIDE, Amigo, NovelD, as well as novelty search methods like GoExplore, which has been used to solve Montezuma's Revenge, they are also in some form open-ended learning processes. Then also people have been looking a lot into strong generalization via environment variations through procedurally content generation. So having ways to basically in every episode to create new situations for an agent to learn from, like in the OpenAI ProcGen benchmark, in Minecraft, in Minigrid, NetHack, and so on. And also in practical applications in robotics, people have been starting to use domain randomization to make their RL policies more robust and to also reduce the sim to real gap when trying to deploy these policies to real world problems, such as controlling nuclear fusion plasma. Similarly, data augmentation methods to again improve the robustness of RL policies. But the important thing here, I think, is that in order to embark on this research and to further advance that research, we need to have very rich and open and complex environments to do this RL research on. And while Atari has been used for a decade now, over a decade, people now started to switch their attention to these procedurally generated environments. So on the bottom right, you see Minecraft. At the top left, you see the Obstacle Tower Challenge by Unity AI. So this is a procedurally generated jump and run game where every time the agent advances on a level or starts a new episode, things will be procedurally generated and look different to anything that the agent has been seeing before. And then another prominent recent example is the OpenAI ProcGen benchmark. This is a suite of 16 different games where in every episode, again, certain aspects of the environment will change, the textures might change, the level layout might change, even the environment dynamics of the enemies might change a little bit. So at that point, your policy, the agent that you train, has to constantly adapt to these novel situations. So all of that is nice. The problem is that the Minecraft environment and the Obstacle Tower challenge, they are both really slow to simulate. Right? These are these kind of rich 3D environments, and it requires a lot of time to basically step through them. The OpenAI ProcGen benchmark that you see in the middle is extremely fast, so that's really nice, but it's actually lacking some of the richness that we would want to see, right, for a open-ended learning environment. So we don't have many different objects to deal with. We don't have much real-world semantics that we have to learn to understand in order to do well in these environments. And that's, I think, limiting the kind of research that we can do with this environment. So ideally, we would want to have something that's as rich and complex as Minecraft while being as fast and, and easy to distribute and run as OpenAI ProcGen benchmark. Well, at that point, we looked into the NetHack game, and we developed the NetHack learning environment. This is a game from 1987. It's a very old game. It's run in the terminal, and it's it has this kind of arcane look where everything basically in this game is rendered using ASCII characters. So you're there's this @ symbol that you see here on the left. You're thrown in this dungeon. It's a very dangerous dungeon. with lots of different ways of dying basically in that dungeon. And you have to find the Amulet of Yender. You have to explore in this dungeon, you have to survive, and you have to descend many, many levels to find this amulet. And what's nice is that this environment, because it's rendered in the terminal, it's insanely fast, right? So you can simulate this environment extremely fast. And that means the environment itself doesn't become the bottleneck of research or of experiments at this point. And at the same time, it's incredibly rich and complex. There are many, many different types of items that you have to learn to deal with, like amulets, weapons, armors, potions, scrolls, and wands and rings and spellbooks and tools and stuff to eat. And that's a really nice sweet spot in terms of complexity and speed at the same time. So let's dive a bit deeper into this. What makes NAACL such an interesting environment for reinforcement learning research? Well, first of all, there's a really clearly defined goal. You should descend the dungeon and retrieve the Amulet of Yender. And all these levels in NAACL, they're procedurally generated. So like in Minecraft, every time you reset the environment, you die and you start from scratch, you'll see new basically dungeons generated, right? You're never going to see exactly the same kind of dungeon twice. As I mentioned, it's very rich. It has hundreds of monster types and items, all come with their own quirky environment dynamics. There's so many things you have to learn about in terms of what kind of monster does what and what kind of item is useful in which situation. And it's so rich and complex that humans generally learn to play this game by reading the NAACL wiki. It's a community-created Wikipedia, basically, of the game of NAACL with 3,000 pages that explains all kinds of things about all these different items and monsters and all kinds of strategies in terms of surviving in this game. In fact, it's such a complex game that there's no recorded instance in history of a human actually being able to learn to win in this game without actually consulting some form of these spoilers. It's also a very long game. There are over 50 procedurally generated levels. If you're an absolutely expert player who's been trained to try to solve this game as quickly as possible, you can win this game in 10 to 20,000 steps. But an average successful run of an expert player would be something like 50 to 100,000 steps. If you compare that with StarCraft 2, where we have 3 actions per second and 50 minutes of gameplay, then that's 2,000 steps. So that's 2 orders of magnitude less than what you would need in NAACL. And as I mentioned, it runs extremely fast. So currently you can get to something like 14,000 steps a second with a distributed reinforcement learning infrastructure using actually just, I think, 2 GPUs based on Impala and TorchBeast. So that means you can train for 1 billion environment interactions a day, which is really a lot. And it's still very popular. There are over 5 million online recorded games of NAACL. And it's open source. That means it's actually still maintained. There's going to be a new version of NAACL coming out, I think, in the next year or so. So people are actually still actively developing it, fixing bugs, adding new things to it. So that makes it quite interesting as well. Yeah, if you ask OpenAI's DALL-E how it looks like when you solve this game, you basically offer this amulet to your in-game deity, and then you ascend to demigodhood. That's how DALL-E imagined this would look like. Okay, so let me try to spend another few minutes to just convince you of how complex this game really is. At some point in the game, the hero is reaching this sea, and within that sea there's Medusa's island, and it's surrounded by water. So basically you have to get past Medusa, which is this @ symbol, this green @ symbol here on the right. So it looks a bit like this maybe. Again, generated by DALL-E. The problem is that when the hero steps into water, any kind of metallic items that the hero might have, like, armors and weapons, they start to rust and corrode, making them much less effective. If the hero happens to have a can of grease in their inventory, they can actually apply the grease on these metallic items, and that prevents these items from rusting and corroding. You could even apply can of grease to a bag or sack, and that makes the entire bag or sack a waterproof container for items. So if you actually have any scrolls or spell books and you step into water, these scrolls and spell books, they will actually become plain, and then there's nothing you can read from them. Okay, so now let's say we have solved that problem. If we step into water, there is a good chance that we'll encounter a kraken, and that kraken can grab the hero and drown the hero, which leads to what's called in these roguelike games an instant death. That means at that point the game is over, you've lost, there's no save games, and you have to actually start to play the game from scratch, from the beginning again. And again, it's going to be procedurally generated. That means you're not going to see anything, nothing is going to be where it was in the previous game, basically. Right? So this is something you would want to avoid as a human player. So what do you do with these krakens? Well, one thing you can do if you have this kind of grease is you can apply that grease on the hero's armor, and that actually prevents the kraken from grabbing and drowning the hero. So let's say the hero makes it to Medusa's island and enters the room with Medusa. Then Medusa's gaze will instantaneously petrify the hero, and that again means it's an instant death and the game has to be started from scratch. What you can do though is you can apply a towel to cover the hero's eyes. That means blinding the hero. Now the hero can actually fight Medusa while being blind. So DALL-E imagines this looks a bit like this. You could also use a mirror, if you happen to have one in your inventory, to petrify Medusa using her own gaze, something like this. Right, so hopefully I convinced you there's really a lot of very complex environment dynamics, even in just this very specific scene somewhere in this game, that it's a very tough benchmark for RL research, because you'd have to have an agent that can actually reason about all of these things in order to do well. So what is the NetHack learning environment? It's a OpenAI gym environment plus some task and a baseline deep RL agent. It's insanely easy to get started. I think at this point you can just pip install NLE, you can import it, start to create an environment, and then step through it. And because it's run in terminal, right, you can just visualize that in your own terminal and start to step through that gym environment and play the game. We have 7 baseline tasks, like finding the staircase on the first level, taking your pet with you, finding some gold, finding something to eat, exploring the game, maximizing the in-game score of the game, or finding the oracle, which is somewhere in the first, I think, 10 levels or so of the game. And as a baseline model, we provide a very simple convolutional network over the symbols that are representing this dungeon grid. We also have a few features like the agent's XY coordinate and health points. And then there's also a agent-centric view that's encoded using a separate convolutional network. And then we use a relatively straightforward deep RL infrastructure to train this agent. As I said, this is something, it's really fast. So it means you can actually train towards something like 1.2 billion steps a day. So then we can look at these different tasks. We can look at different metrics. I'm not going too much into details, but basically you see actually learning picking up. So the agents start to learn to, for example, maximize the in-game score of the game by killing monsters, by descending down the dungeon levels. You can play with different character classes. So here we have a monk, a Valkyrie, a wizard, and a tourist. Different character classes are more or less difficult to play for humans as well as for this AI. And overall, I would say, this makes some progress in the game, but it's a really, really difficult game. And it's not super impressive at this point, right? If you never have heard about NetHack before and you start playing this evening, you'll see that it's actually a really difficult game. So if you want to get to, let's say, a mean dungeon level of level 5, then probably you need to practice for a few hours. So our AI is basically not terrible at this, but there's still, tons of room left in order to actually win this game. So let's have a look at this NetHack wiki. So as I mentioned, there's this fantastic resource that's created by the community where you have over 3,000 documents explaining you all the things you want to know about NetHack, right? All the different, for example, weapons and their damage, the material they're made of, what kind of skills the hero would have to have in order to be effective with these methods, with these weapons. Human players would use this NetHack wiki a lot, right? It, for example, tells you for all the different monsters, all kinds of base statistics. It gives you some strategic advice in terms of what you should and shouldn't be doing when you're encountering these monsters. And funnily, actually, a lot of these Wikipedia pages or NAACL wiki pages point to the actual source code of the game. So if you then want to dive deeper into how exactly the environment dynamics work, you could actually look at the C code to understand what's going on. And that was actually how people in the 80s and 90s were learning about winning this game. They would actually, because the NAACL wiki didn't exist at the time, they would look at the source code to get a better understanding of what's going on. So now you might ask, okay, do we really need the wiki, right? Couldn't we just try to train an RL agent from scratch that eventually will win in this game? And I think the intuition at this point is that, yes, you would probably want to have an agent somewhat conditioning on information in the wiki, because there's so many ways you can die in this game. There's so many ways you can die in so many stupid ways in this game that the NAACL wiki even has a document just about that called Yet Another Stupid Death, with an abbreviation that the community is using a lot. So yes, you need the NAACL wiki. And we ran this NAACL challenge at NeurIPS last year, where we invited both deep reinforcement learning researchers as well as symbolic bot makers to participate, and we didn't provide any constraints in terms of what kind of submissions people could put forward. And quite interestingly, we found that deep RL agents do much, much worse at this point than the symbolic bots that humans can write. And the symbolic bots that humans write, they are not perfect. They don't get very far in the game either, but at least humans find it easier to convey their domain knowledge about the game and their intuitions when they write code for these bots. Then they find it easy to provide these intuitions and domain knowledge that they have to these deep RL agents. So that's the picture right now. So symbolic bots outperform deep RL agents by a factor of 3. And we're very excited to see how this will unfold over the coming years, when hopefully more deep RL researchers try all kinds of different methods that hopefully at some point will catch up and do better than handcrafted bots. Okay, so I talked about the NAACL learning environment. The problem with the NAACL learning environment is that it's an extremely, insanely difficult environment, as I mentioned. And in RL research, sometimes you want to start a bit smaller, right? You want to on the spectrum of basically problems you could use to prototype your RL approach, you want to maybe start on the other end of the spectrum, on some kind of toy task, right? And then when you see your method working or failing, you might want to start changing these tasks, or you might want to start making these tasks more complex. And for that, we created MiniHack. And it's basically a sandbox for open-ended reinforcement learning research, where you can design all kinds of problems of all kinds of difficulty on the spectrum. And the way this looks like is you have all kinds of tasks that you can create in this MiniHack environment, and it's using NetHack as an underlying engine for the environment dynamics. So the way this looks like is that you have almost like a domain-specific language that defines basically environments. So this domain-specific language, you can see here an example on the left. First, you would create a map. You could randomly generate one, or you could even draw one yourself using ASCII characters, like I did here on the left. Now on the right-hand side, you see how that map would look like, or this environment would look like, when we actually load it and render it in NetHack. You can use all kinds of different dungeon features like walls and floor and lava and water and whatnot. You can even create larger maps. In this case here, I'm creating a world map, and I'm purely creating that by writing these ASCII characters that you see on the top left. Okay, so once we have a room, we can start to fill it with stuff. We can, for example, add a bat. We can add a longsword. We can create a staircase down that's going to randomly move every time we're resetting the episode. That staircase is going to be somewhere else. We can add some random things to eat. We can add some random monsters. We can randomly replace some of the tiles with trees. And we can randomly create a lava or water or ice river that goes from the top left to the top right. So now we basically have created almost like a probabilistic program that every time it's run, it would create a different environment, right? So every time we now run this code on the left, it will create a different environment that we can then use to train and test our reinforcement learning agent. So it makes it extremely simple for anyone to create a very rich, complex, and big space of environments from just a few lines of code. You have all kinds of high-level instructions you can also use to create these levels. You can, for example, create labyrinths using the maze walk command. You can connect rooms using random corridors using this command. You can access the hundreds of different monsters and hundreds of different objects in NetHack and populate your environments with those. You can use all kinds of different dungeon features. And yeah, it makes it really easy for anyone to create very rich environments. As part of the observation space, we're now not just providing the symbolic observation space of NetHack that you've seen before, but we also provide this pixel rendered observation that you see on the left, as well as, and that's maybe most interesting for this community here, you can actually also render or provide as an observation a natural language description of anything that the agent is seeing, right? So instead of visualizing the observations in pixels or symbols, you can actually you can just get natural language descriptions of everything. We also have in NetHack the textual messages that you see here on the top of this screenshot at the bottom. So that is a really interesting modality because it gives you insights into what just happened in the game, right? So you attack a jackal in this case, and the game would tell you, you actually missed that monster, now that monster bites, and then your little dog friend also tries to attack that monster and also misses. The action space in NetHack and also MiniHack is vast. There's over, I think, 70 actions that yeah, all behave very differently, and you have to learn about all of them if you want to do really well in the game. And we have two kinds of interfaces to create these levels. One is this description file interface that I already showed you. This is here on the left. We also have a Python interface. So if you don't want to learn this description language, you can still draw your own levels and then start to populating it with all kinds of monsters and items using this Python interface here on the right. As part of MiniHack, we also provide predefined tasks. On the left, you see all kinds of navigation tasks that can be extremely challenging, like the labyrinth navigation task that you see here. And at the bottom left, you see basically a task where you have to avoid a very powerful monster. It's like a hide and seek task where you have to hide between trees and clouds to make your way to this staircase down on the right. And we also have skill acquisition tasks. That means tasks where you really have to learn how to utilize all kinds of different skills in order to do well. Like, for example, here in the middle, you see this lava river separating the left from the right side of the room. And you can, for example, learn how to use a ring of levitation to fly over that lava, or you can put on boots that allow you to jump over that lava, or you could even learn to use a frost horn to turn that lava into stone and then just walk over the lava crust to get to the staircase. So these are very difficult exploration problems for RL, right? Because on the left-hand side, maybe you can have an exploration method that rewards the agent for discovering new parts of the level, whereas on the right, really the exploration happens in the kind of skill acquisition of learning how to use these different objects. So where can MiniHack be used? It can be used for classical reinforcement learning research, for investigating transfer learning, for example, between different MiniHack environments, or eventually at some point also transfer learning from the MiniHack environment to the full game of NetHack. It can be used to investigate unsupervised skill discovery, unsupervised environment design, and language-assisted reinforcement learning, which is the thing that I'll be focusing on in the remainder of this talk. So I'm going to talk about a paper by Jesse Mew on improving intrinsic exploration with language abstractions. And the idea here is that for many environments like mini-grid or mini-hack environments, exploration is insanely difficult. So although these are relatively simple still grid worlds, you can easily construct problems where random exploration or even state-of-the-art exploration methods would miserably fail. So in the absence of rewards, how do we encourage exploration in RL? We can't wait basically for an agent to randomly do the right actions to receive a reward. We have to intrinsically motivate the agent to learn about the environment dynamics, to learn about what kind of things the agent can do in the environment before first encountering any reward. And basically we want to reward an agent for visiting novel states in the environment. So that's a relatively established approach. And the question here is, how do we measure novelty? We could count the observations, right? So that's a very established approach. But in large environments, that becomes a problem because you basically will see new states all of the time. So if you count something, you might just assign a count to 1 for everything you see. There are some ways to deal with this. There's random network distillation world modeling that allow you to learn representations of the states and then measure novelty in this learned latent space. But even there, it is quite tricky. All right. So another problem in using state-based novelty is that you could have a stochastic environment with what's called a noisy TV. That means every time the time advances in the environment, the agent will see a new observation, and it will be attracted to these sources of stochasticity in the environment, but it won't really meaningfully explore the environment to expand its skill set. So one example is given here. We have this procedurally generated multi-room environment from Minigrid, and every time the agent experiences a new episode in this environment, the room layout might completely change. But what might be important here is that the agent is in front of a green door, right? So we could use the language description that the agent should go to the green doors in front of the green door as an abstraction over the actual state representation. So that means they are actually different states, but actually they have, in that way, same semantics in that the agent is in front of a green door. Another example is like, let's say we want to make an omelet in some 3D environment, right? We might be actually randomly wandering around, and lots of these states in this environment would be really not useful for actually the target of making an omelet. If you knew that in order to make an omelet, you'd have to stand in front of a stove, right? You could massively prune away the states that you actually consider for exploration in this environment. So not every novel state is going to be useful, right, if we have a specific task at hand. But the main point here is that language is a really powerful and flexible way to specify the relevant features of an environment that we should be using for novelty search and for exploration. To give you an example here on the left, we again have this mini-grid environment. We could have language descriptions such as, you should be going to the green door, you should pick up the yellow key, or you should put the key next to the yellow door. And none of these might really have something to do with the actual concrete task that you have to solve in this environment. But if we keep on challenging an agent to accomplish such language descriptions as seen here on the left for a long time, right, it will experience or learn to master basically anything there is to be mastered in such an environment. And the same goes for this much more complex, much more harder environment here on the right, mini hack. We have this task here to fight this minotaur in this room, but if we just go to the minotaur, we're going to die because the minotaur is a very powerful monster. But there's actually going to be a wand of death that we can zap at that minotaur, and then the minotaur is dead, and we can just go to the goal on the right. But the problem again is here that the agent can't learn to randomly try, or can't learn to fight the minotaur by just randomly trying out things. It's going to take ages to randomly basically pick up the wand and zap it in the right direction and whatnot. But we can break down this exploration problem by giving the agent early in training goals like, go to the staircase, or see if you can find a wand, or try to zap the wand, and try to zap the wand in all kinds of directions. And if it masters that, right, then it can at some point also learn to kill this minotaur. So in previous work, lots of different researchers have already looked into using language for RL, but linguistic exploration methods often compare to relatively naive baselines in very isolated environments. So the question that these existing works have tried to answer is whether language can help exploration. What we try to do here instead is to actually augment existing state-of-the-art exploration methods with language abstractions, and then evaluate them on common RL benchmarks, really an apple-to-apple comparison. So what we are interested in answering here is when does language actually provide a better or alternative way to parameterize existing state-of-the-art exploration methods. The two state-of-the-art methods that we are using here are Amigo and Novel D. They have both been published last year. And we present two language augmented variants of these two exploration methods and show that they drastically improve exploration capabilities. So the way we formalize this is we just start with a normal MDP, and then we augment that with a natural language annotator. So it's this function that given states can give us some language description of the state that the agent is in. So it could, for example, in the case of mini-grid, actually tell us the current goal that we want the agent to achieve in natural language. It could say, go to the door, or maybe it doesn't say anything, or it maybe says something like pick up the key. And then we have an intrinsic exploration method that maximizes the sum of the intrinsic and extrinsic reward. Okay, so let's look into how that works for this Amigo approach. So in Amigo from 2021, what happens here is that you have a student policy that tries to act in the environment, and that is goal conditioned. The student gets intermediate goals, such as going to specific positions in that grid, and then gets a reward for achieving these intermediate goals. And when it goes happens to stumble upon extrinsic reward, it then gets that extrinsic reward from the environment. Then we have a teacher that starts to propose certain positions around the agent, and it tries to make that gradually harder and harder. That means the teacher is rewarded for proposing goals that are not too easy and not too hard to achieve by the student. So here, this is parameterized by a specific threshold in terms of the number of steps that the agent has to take. And that difficulty threshold is automatically adjusted while the student becomes more adept at solving the task. So in the beginning, right, the teacher would propose positions really close to the agent. So basically the student agent would just learn to move around in a room. Later on, the teacher would propose goals that are in different rooms. So that in order to get there, the student would have to, unlock a door, or might even have to find a key to unlock a door. And then later on, it will actually propose really difficult positions that might correlate very heavily with the actual extrinsic goal that the agent is supposed to achieve anyway in this environment. And now basically what we do is we turn that into a language augmented version of this Amigo approach, simply by instead of using these coordinates in the environment, we actually use these language goals that one could achieve in this environment. Right, so we assume that we have this language annotator that gives us, given a state, a language description, and we don't assume that we have access to all achievable goals in this environment in a specific episode. Instead, we learn a grounding network that, given the kinds of goals that we've seen so far being achieved in previous episodes, tries to predict, given the current observation, what are likely achievable goals in the current situation. And then from those, we select one and we give it to the student. And if the student, again, is achieving the language goal, so it achieves to, let's say, go to the yellow door, it achieves to pick up a certain key or to unlock a certain door, the student gets an intrinsic reward, and also the teacher gets a reward for proposing a goal that's, again, not too easy and not too hard to achieve. And in mini-grid, we can look at all the different messages that have been basically collected over this training run, and there's really a lot of them. And mini-hack, there's also lots of them for the specific mini-hack task. And they do really cover a lot of things, like, bumping into a wall, or finding a staircase, or finding a wand, or zapping a wand, or picking up a specific item like a weapon or a piece of armor, right? So lots of things that you really have to learn to do well if you want to do achieve something in this game. Okay, so then we can compare Amigo, again, the state-of-the-art exploration method, with this language equivalent, and we see not so many improvements in terms of these navigation tasks where you really have to just mostly walk around, but we see quite dramatic improvements when it comes to these skill acquisition tasks, where you not just have to learn to visit certain parts in the environment, but you actually have to learn to deal with certain items, right, or certain monsters in certain ways. So overall, in this mini-grid and mini-hack benchmark suite, we see a 45% increase in terms of extrinsic reward achieved by this language variant. So that's a pretty significant result. We can then also look at the kind of curricula that is induced by this El Amigo approach. So we can see what kind of goals are the ones that the teacher proposes to the student over the course of training. And we see in the beginning, these are relatively simple goals in this case of mini grid, right? It's like open a door or go to a door. And then later on, you'll see the agent actually starting to pick up the key or proposing to pick up the key. And then later on, even picking up the ball, which is the goal, the extrinsic goal of this environment. And similarly, in MiniHack, you see the agent in the beginning getting goals proposed, like trying to zap a wand or finding a staircase. And then later on, you see the agent actually using the wand to kill the Minotaur, this blue goal, basically, that starts to be proposed later. And then even further on, we're mostly basically encouraging the student to actually find the Minotaur corpse after it has killed the Minotaur. So now let's switch over to the other state-of-the-art exploration method that we meant with language goals, Novel D, and then its equivalent language, Novel D. So in Novel D, the agent is rewarded by transitioning into states with higher novelty. Novelty is count-based, and we have a difference in novelty between successive states, as well as a novelty bonus that's episode-specific. And the problem here is, again, that once we go to more complex environments like MiniHack, then just visitation counts of states doesn't help at all, because there's stochasticity in the environment, there's randomness in terms of where items are placed in the environment. So you see a lot of novel states and novel state transitions. So that means most of your counts are going to be 1 anyway, and it's not going to be very informative. However, we can quite easily augment that with language annotations. So here again, we assume we have this annotator, and now we just add basically another Novel D bonus that's based on these counts of the language utterances that we've seen in the environment. So both in terms of transitions as well as within episode boundaries. And then we can again compare the two approaches, the baseline Novel D approach and language Novel D, and we see again very much the same picture. So in these poorly navigation tasks, we don't see much of a difference. We still see improvements, but they're not that as drastic. Whereas then in the skill task, we see very drastic improvements. And here we now have a improvement of 85% over the Novel D state-of-the-art exploration method. So again, a very significant result. And then as before, we can see how the curriculum over these message goals looks like. And I guess as before, we see here the agent, for example, getting encouraged to zap a wand at some point, then figuring out how to use the wand to actually kill the Minotaur, and then even trying things out like lifting the Minotaur. That again is something that's not really useful for the extrinsic task, but you should still learn about these things, right? If you really want to learn anything you can learn about this game, and then to eventually win in the full game of NetHack. So yeah, to summarize, I think there's really an interesting shift from static RL problems to actually environments that are more open-ended, that really test for systematic generalization. And I think that's really exciting as a field, because that means RL gets closer and closer to actually being applicable in real-world problems. And open-ended learning mechanisms, I think, play a very important role in finding effective curricula. And we hopefully, as we've seen, language seems to be an extremely valuable modality for state abstractions and novelty search. So I'm pretty sure we'll see much more of that in the coming months and years. So with that, thank you. And yeah, let me know if you have any questions.
Hi, I don't know where Raj is.
Yep. Sorry, say again.
Thank you. I know I was waiting for Raj. I don't know where he is, but thank you for the talk.
All right, yes, I'm back. Yeah, thanks, Tim. So did we have questions in the room first? Okay, please come up here.
Oh, hi, I'm Shreyan from CMU. It's a great talk. So you mentioned something about like NAACL wiki. So I'm wondering if you have any works on like ongoing work or like already published work on that already, on what's your thoughts on how to leverage that? Because it looks like a little bit like the structure, semi-structured knowledge, or kind of what people are doing nowadays for open domain QA and retrieval algorithm stuff. So I'm wondering, like, what's your thoughts on this? Thanks.
Yeah, I think that's a fantastic question. So I feel like, to me, it's a holy grail of how do we utilize this NetHack wiki for efficient exploration in this environment. And I don't think anyone has an answer to this at this point. The two things we started doing was we had a initial project on trying to just encourage slightly more meaningful exploration in NetHack instead of these kind of random sampling of actions that you want to explore. In certain situations, you could, for example, use the NetHack wiki or even just word vectors, right, to figure out what you should be trying out if you're in front of a locked door. NetHack gives you these over the actions you could do in front of a locked door. You could some your inventory, none of that in terms of that door, but you could also you could start to use that key to unlock the door. You could try to kick in the door, and if we use word representation.
Okay, I think we lost Tim for a second.
Representations within NetHack wiki could be a way to get this kind of bias distribution over the kinds of actions we want to use in NetHack. The other project we had was we had a master student actually looking into whether we can use Q&A systems to have a basically tutor, natural language tutor that, given natural language questions, would tell you what to do in NetHack. So how well do these open domain Q&A systems transfer over to the NetHack wiki, very domain specific text? And actually works quite well. We haven't released that yet, but I think that kind of works. So maybe the hope is at some point, if our open domain Q&A models get better and better, maybe we can hook them up directly with RL agents, right? If we have, for example, an index over neural representations of the passages of NetHack, we could have the neural representation, internal representation of an RL agent, then directly kind of query that neural knowledge base to retrieve information that might be useful for the agent. But I think that's still, very, very much out there. So I'm not sure how to best do this.
Cool. I think one more question. All right, Mitch.
Hi, this is Michi from IBM. It's interesting to see that the kind of the game I played long time ago is now the target. But so I remember that people really need the kind of spoiler to solve the NetHack. And as you introduced, the reading and understanding wiki is important. So having given that for your mini hack, what's the name? I don't remember the mini hack environment. Yep. Why don't you just produce that kind of wiki for the different type of games, so that we can just try to emulate such kind of hints or wiki, which I don't know, some instruction is maybe corresponding to that, but it might be better to simulate or emulate that what we can see in a NetHack, that we have a game and wiki spoilers. So why don't you have a spoilers for mini hack?
So we had this paper with Victor Zong, which was called Reading to Fight Monsters, where we procedurally generated environment dynamics, and we also generated a synthetic wiki on the side, and then we did kind of wiki conditioned RL. So that's a paper I think published at ICLEAR 2 years ago. And at some point, I mean, that worked, and then I think we're a bit dissatisfied with the fact that here we synthetically generated the wiki, right? So I think now really we need to move over to research where we actually work with the messiness of an actual game wiki and learn how to explore better based on such a wiki. And what we could do, and I guess that's maybe what you're suggesting here, is we could use MiniHack where we have smaller tasks where we could then use specific paragraphs on NetHack wiki that we provide to the agent, instead of having this grounding problem where if we're in the entire game of NetHack, we have this enormous NetHack wiki, we don't even know which kind of documents are relevant for certain situations in the game. With MiniHack, we could have the scope such that we know there's only 2 or 3 relevant paragraphs to read that will be useful in order to solve the task. And I think that would be an interesting project. I think that would be an interesting way forward. If we can't solve that, and we have no hope that we can learn to play the full game of NetHack using the full NetHack wiki.
Cool, thanks, Tim. In the interest of time, I think so. Could you ask them offline in the Zoom chat? So we're sort of already running a little bit behind schedule. So is Hal on the call? All right, thank you, Tim. That was, I mean, there's people clapping here. I don't know if you can hear us, but yes. Okay. I have the call.
Yep, I'm here.
Yes, hello, Hal. Okay, so this is our next talk. We're going to have Hal Dame talking about training agents to learn to ask for help in virtual environments. So Hal is a professor at UMD in the CS department and is also a senior principal researcher at Microsoft New York. His main focuses are in NLP and ML. He doesn't really need an introduction at this conference, but I am going to, this is the intro anyways. So Hal's sort of 2 main research questions are how can we get computers to learn through interaction with people, and how can we do so in a way that minimizes harms in the learned models? So with that, I'm going to turn it over to Hal.
All right, thank you. Let me share my screen. All right, can you see all right? Can you see me and see the slides?
Can't see, okay. Yes, all right.
All right, cool. So thanks for inviting me. I'm really excited to, I feel like I can't say be there because I'm not, but to be able to participate remotely. I was hoping to be able to be in person, but it just didn't work out. So today I'm going to talk about a bunch of work that we've done over the past couple of years on training agents to learn to ask for help. And as part of the framing that I want to take here, I want to think a little bit about 2 possible reasons why we might be sort of doing AI research. So one, which I think is maybe the dominant view right now, is sort of this notion that we want to build replacement humans. So things that can do the jobs that people can do as well as people. And this is certainly the view that's been taken over by all of Hollywood, essentially. There's another view, which is sort of the more human-centered view, which is that I want to build AI technology so that I can build tools. And so here, we have sort of like a fulcrum and a lever being used to lift a rock. This is obviously a very simple tool, but it's something that lets people to do something that they would be unable to do otherwise without that tool. And so I want to focus largely on this second case. And I hope also to convince you that working on this second case is actually quite interesting and exciting. And I hope that one of the perhaps impacts of this talk is that more people get excited about thinking about building agents to assist people rather than replace people. So this is not a new idea. There's a bunch of papers and a bunch of books. Here's a quote from Marty Hurst. So she says, in the last few years, a series of well-publicized debates argued the merits of total automation of user needs via intelligent agents versus the importance of user control and decision-making via interfaces. And this is certainly, well, my phone just thought I was talking to it. So this is certainly something that, I've heard a lot over the past couple of years. The thing that might surprise some people here is that Marty actually said this back in 1999. So I think, despite this question already being raised about, sort of like fully automated systems versus useful AI-infused tools, the field has sort of clearly gone one direction, but maybe we can sort of pull it back in a slightly different way. So if you sort of buy this premise that it's interesting to think about agents that help people rather than replace people, then a bunch of questions arise. So one is, what does it mean to be helpful? What are tasks that people want to solve where they're unable to do so on their own, but might be able to do so with a little bit of assistance? We obviously need systems that people trust, otherwise they're not going to use them at all. And I think importantly, most people in the world are not AI experts, which means that any sort of interaction between a person and an agent that's trying to help them can't rely on things like, people providing reward signals or people providing, hours of demonstrations or things like that. So we need some way of communicating with these agents that doesn't rely on specialized knowledge. So I think games are actually a really interesting area to pursue these sorts of questions for two reasons. So one is, sort of obviously the business reason, right? Like games are a big business. Increasingly, there are things like non-player characters in games that are supposed to interact intelligently with people who are playing the games. And so from like a very applied perspective, I think there's a lot of value in thinking about how you can use AI to build assistance in, say, Halo or whatever your favorite game is these days. The other is that, they provide a useful test bed for building agents. I remember back when I was a kid, and I'm totally going to date myself now, but I actually did play Zork. And I remember I just had like reams of poster paper where I would like draw out maps and I would make notes to myself on like, if you take this action in this state, like what happens. And, I think without that, at least as a kid, the game was essentially impossible to play. And you could imagine having agents that can fulfill that role, right? So like not trying to play the game themselves, but trying to provide some sort of aid to a person who's playing the game. But if we're going to do this, like we need the agents to be able to communicate with the people who are playing. So communication has been studied by lots of people. So in biology, there's a lot of study of associative communication. So this is things like providing low-level electrical or biochemical signals. When you get up to higher primates, you get referential communication. So this is when you start having a symbol system and you're able to reference entities in the world. And then sort of at the highest level, we have inferential communication. So this is where the entities, in this case, people, for the most part, have models of the world and intentions, models of intentions of themselves and others, and they use these models to infer meanings pragmatically. Okay, so right now, I think a lot of where we are is in associative learning. So we have agents that learn from, essentially these like kind of fake biochemical signals that say like, oh, what you're doing is good or what you're doing is bad. And I think both reinforcement learning and imitation learning and learning from demonstrations and all sorts of things fall in these categories. And so what we've been trying to do is push a little bit further up this, this communication pipeline. Okay, so I think the first sort of work that we did in this area that has nothing to do with games at all was this work with Sudha Rao on learning to ask clarification questions. So the idea here was when people, for instance, post to like a Stack Exchange or something, they often ask a question that's insufficiently precise. And so the question was, could we help those people refine their posts to make it more precise so that they could get an answer? And so here we have someone who's trying to configure path or set of environment variables. There are a bunch of questions we could ask them. So we could ask them, what version of Ubuntu do you have? What's the make of your Wi-Fi card? Or are you running some specific version of Ubuntu? And so the idea was that, here the first question is probably the best one. The second one's not really relevant to what the person is trying to accomplish. And the third one is relevant, but if you get a yes, no answer and the answer is no, that provides almost no useful information. So we formulated this under this expected value of perfect information idea, where we want to ask a question given a prompt so that in expectation over the possible answers that you might get to that question, the utility of getting that answer is maximized. And so in order to implement this, we had to make some sort of architectural design decisions for how to estimate the probability of an answer, and then how also to estimate the utility of getting that answer. So I won't go into detail about how we did that. You can read the paper. It's a bit old at this point. But basically the main thing we saw, so here green, the bar on the right is this expected value perfect information approach. And the thing that we see is that this improves fairly substantially across other neural models that share the same architecture, but are not actually trying to maximize the value of information. And you see this in various measures like precision at 1 and mean average precision. Okay, so shifting from this into more of an interactive setting, a setting that starts looking a bit more like games, we worked on sort of extending a bunch of these ideas to these navigation style tasks. So this is work by Con Wen that was at UNLP a couple of years ago. And so here we have a person who asks their little robot buddy to help them with something. So in this case, they might ask them to find a mug, and then the agent has to navigate this 3D simulated environment in order to accomplish that task. So it turns out that if you just set agents on this task on their own, their success rate is in like the single or maybe double digits. It's really, really quite poor. And this is, I think, an example where, yes, we can try to fully automate this thing. But if we're willing to actually start thinking about a little bit of communication between the person who's issued the task to the agent and the agent beyond the issuing of the task, we can actually do a lot better. So this is something people do all the time. If you're in Seattle and you've never been to Seattle before and you need to find your way, and I don't know, your Wi-Fi is down or something, you can ask a person on the street for help, or you can ask Google Maps for help for that matter. And so what we want to be able to do is to try to give agents, the artificial agents, the same sort of functionality. So the way we did this in this paper is the agent has just basically one bit of communication. So the agent can basically raise its hand and say, I need help. And at that point, in this case, a simulated virtual human will look at the task that the agent's trying to solve, look at the environment, and give them some instructions that help them make progress on the task that they're trying to solve. So in this case, maybe the robot's trying to find a mug. It gets lost, and the person gives the robot a little bit of assistance on how to make progress toward that task. Okay, so the way that we do this is at every time step, first the agent has to decide whether it wants to ask for help or not. If it doesn't ask for help, then it just executes a navigation policy, which chooses an action of those that are available to it in the environment. Otherwise, it decides to ask a question, in which case it raises its hand, it receives a response, and then it goes on to the next time step. Okay, so to train this, we're going to use some flavor of imitation learning. So for the navigation policy, it's pretty easy to come up with a good teacher. So in this case, for the teacher for the navigation policy, we just say whatever action takes you to the next point in a shortest path to the goal from wherever you are is the action you should take. And so we can train this dynamically using sort of off-the-shelf techniques. Asking for help is harder because we don't have any sort of ground truth asking for help that we can try to imitate. And as I'll talk a little bit more about later, mimicking the sorts of questions that people might ask is perhaps not the best approach here, because information that's useful to a person might not actually be the information that's useful to an agent, and vice versa. Okay, so how did we do this asking? So we take two components. The first is, I think, sort of the obvious idea, which is an uncertainty-based component. So if the navigation policy's entropy is sufficiently high, then our quote unquote expert asker that we're trying to imitate will ask for help. It turns out that alone doesn't do very well, possibly because these models are all very poorly calibrated, and so measures like entropy are only sort of modestly useful. So the main idea was this progress-based analysis. So the idea here is we want the agent to estimate whether, from its current state, it is likely to make progress or not in the future. So at its current time, it can't know that. But once a training episode is over, it can retroactively look back at the various states in its trajectory and compute whether from that state on, it made progress, i.e. got closer to the goal. And if it didn't make progress, then we use that as a training signal that it should have asked for help at that point. Okay, so how well does this work in practice? So in the environments that we evaluate on, there's both scene environments. So these are houses that the agent has been in before, but with new tasks, and there are unseen environments, so places it hasn't been before. So if the agent just randomly walks, it succeeds about 0.5% of the time. So that basically doesn't work. If you train purely with imitation learning and not the ability to ask questions, you get 17% success rate in seen environments and 8% success rate in unseen environments, which is not particularly compelling. This was a few years ago. These numbers have gone up in other papers, but they're still nowhere near where a system would become useful. If you're able to ask for help, but you don't get language feedback and you only get image feedback, so the person says like, oh, here's an image of the place you should be going. This helps a lot in scene environments, largely because the agent has probably more or less memorized the layout of the scene environments. And it helps a bit in unseen environments, but not nearly as much. And then finally, if you get language feedback, this helps, sort of slightly more in seen environments, but it helps dramatically in unseen environments. And arguably, this is because language has this nice property of being able to generalize, whereas images are sort of just static images, and either you've seen that part of the house or you haven't. Okay, so the big takeaway here is that the hardest task we had was figuring out when to ask for help. And when you're able to do that successfully and you're able to get language feedback, the agent with a relatively small amount of help from a person can make substantially more progress than one that has to operate entirely autonomously. There's sort of an obvious weakness to that work, which is that the robot or the agent wasn't able to ask anything more than "I need help." And so you can imagine that you might be able to do better by having an agent that can ask for a specific type of help. So this is a paper at ICML next week that Khan will be presenting. So if you're missing ICML, now you don't have to go to ICML, because I'm sure this was the only paper you would want to see at ICML. So the idea here was, how do we train an agent to ask more specific questions than just "I need help"? So we looked at a bunch of examples of questions that people ask in similar environments, and they tended to fall into one of three categories. So either they want more information about where they are, they want more information about what they're trying to achieve, or they need some help along the way. So those are the three. And as I mentioned before, you could imagine trying to solve this by imitating questions that people ask. So that was like the work at the very beginning that I talked about with Sudha. But people are very rarely going to ask for more information about where they are. Like, unless the lights are off or like something weird is going on, like people are pretty good at like understanding where they are. and they're much more likely to ask for the other things. But for an artificial agent, that's not necessarily true, right? So it has imperfect sensors, its vision system is sort of far from ideal. It's totally possible that this sort of information would be far more useful to an agent than it would be to a person. So we don't want to just try to imitate the questions that people would ask. Instead, we want to have the agent learn to ask questions that would actually be helpful to the agent itself. So these are the three types of questions that they can ask for. So in the upper left, we have the goal question. So this is basically tell me more about the goal location, in which case you get a response like the rice cooker is in the kitchen next to the sink. You can ask for more information about your current location. So here someone might say you're in a living room next to a couch. Or you can ask for a subtask. So this is basically a request for sort of help along the way, where the assistance will come in the form of some sort of information that will help the agent make progress toward the goal. So implementationally, the way we handle subtasks is the agent has a stack. When it asks for a sub goal, it pushes it onto the stack. When it thinks it's completed the sub goal, it pops it off the stack. And when it finally sort of pops the main top task off the stack, it declares that it's completed. So we write all this down as partially observable MDP, and we train based on optimizing success rate in the environment in a similar sort of setting where either the agent asks for help or it navigates, and if it asks for help, then in the next step, it might be more likely to navigate. Okay, so the evaluation here is similar but slightly different to before, which unfortunately means that the results aren't directly comparable. But the tasks are of the form find some object in some room. And we're doing this in a simulated sim to real transfer scenario. So what does that mean? So in sort of a perfect information setting, you could imagine that the agent receives information about all the objects and features in the room that it's currently in. What we do is we essentially simulate an imperfect vision system where a bunch of these are missing, only the most frequent objects are actually detected. And if it wants information about let's say this piece of art on the wall that's labeled question mark, question mark, question mark, it has to specifically ask for that information, in which case that feature value would then get filled in its representation. Okay, so here are some results again, according to success rate. Let me walk through these sort of one at a time. So let's start with the left group of bars. So this is known environments, but where the agent is starting someplace new that it's never started before. And so the blue bar is how well does it do when it has to operate completely with the imperfect information. So it can't ask any questions. So that's sort of a baseline. The red bar is how well it can do when it has perfect information and doesn't ask questions. So that's basically, it's kind of a skyline, but not quite. We also implemented a rule-based model for asking questions, which asks questions with the same distribution as the agent that we learned based on the POMDP framework. And so that does better, but sort of not quite as well as perfect information. And so then the green is ours. So the big difference between yellow and green here is they're both asking for the same amount of information. The green one is just doing a better job at asking for information. So the thing that's interesting here is that in unseen environments, okay, first the success rates are all quite low. But in unseen environments, the learned model actually outperforms the model with perfect information. And the reason this happens is because it can ask for sub-goals. And especially in unseen environments, having access to sub-goals can make a big difference because the paths that you're usually trying to follow are quite long, like 10 to 20 steps on average. And if you just sort of wander randomly, you're very unlikely to make progress. Okay, so there's sort of this obvious question, which is like, you know, is it just enough to get the information, or does the model actually learn to ask for what it needs? So here what we have is we have what we call a cooperative and uncooperative responder. So the cooperative responder provides the information that the agent asked for, and the uncooperative responder provides some information which may or may not be what the agent asked for. And we see across all these environments about a like 4 to 7% improvement when the agent actually gets the information it asked for. So this suggests that it is actually learning to ask for what it really needs. There's also a little bit of sort of interesting stuff that happens across an episode. So what we're looking at here, so the x-axis is how far through a single trajectory is the agent. So on the far left, you have basically its starting location, and the far right, you have its ending location, like right before the goal. And so what we can do is look at, averaged over all of the validation data, what type of questions is it asking at various points in its progress. So what we see is that at the very beginning, it's sort of an information gathering mode. So it basically says, tell me about my state, tell me about the goal, excuse me. And then at that point, once it sort of knows where it is and where it's trying to get, it increasingly asks for sub-goals and decreasingly asks for information about the current state. It basically never asks for more information about the goal state. It gets that at the beginning and then continues. And then toward the end of the episode, it tends not to ask for very much at all. Okay, so I guess these were 3 papers I talked about. So in all of these, I've been talking about asking questions, but there's obviously more to communication than just asking questions. I'm communicating now and I've asked very few questions. So, you know, why is communication useful? Well, it's useful to establish common ground. So, you know, I don't know, after this talk, hopefully at least a couple of people have some questions to ask. Those questions will be now grounded in this common ground that we all now share because of this communication that I'm doing. There's sort of a side goal, which I'll come back to at the very end, which is that having agents that having the ability to communicate in the other direction. So we're going to be talking here about agents describing their own behavior rather than asking questions about behavior, is that a lot of this work now requires sort of non-trivial effort in doing human evaluations. And the sample complexity for a lot of these algorithms is sufficiently large that you really don't want to just like fire up a mechanical Turk job and have it try to learn from scratch. Like you will spend some ungodly amount of money if you try to do that. And so one of the things that we're trying to do is to build simulators that will be sort of a stepping stone that can be used to pre-train agents before you actually do a human style evaluation. Okay, so what are we going to do here? So this is work with Lingjun Zhao and Khan that is not published, so you won't find this anywhere, but I'm happy to answer questions about any of this. So here we have an agent which has executed some path, so that's the green squiggle, and we're going to ask the agent to describe the path that it took. And so, you know, okay, so why might we want to do this? So one is so that if the agent and the person that's using it need to sort of clarify things, the agent needs to describe what it's done and where it's been and what it's going to do next. And then the other reason is because we want to use this in order to do simulation. Okay, so there's an obvious approach here. The obvious approach is take one of these data sets that has paths paired with language utterances, and instead of training a model to map from language utterance to path, train a model to map from path to language utterance. So that's certainly a reasonable thing to do, and there's been a couple of papers that have done exactly that. But this is not necessarily the best way to communicate. So this is an example from this Goodman and Stuhlmuller paper 10 years ago. If you have this, this stick figure, which has 3 apples, one of them is hidden in a bag, and the stick figure says, some of the apples are red. And I ask you, what color is the apple in the bag? Most people will say that it is not red, right? And like, why do most people say that it's not red? Well, because we sort of imagine that if it was red, then the person would have said all the apples are red. And so the fact that they chose instead to say some of the apples are red suggests that there's at least one that's not. So how is it that we do this? So the rational speaker model basically says, like, okay, when I'm speaking, I'm going to imagine a listener who's listening to what I'm saying. And I'm going to imagine how they will interpret what I say. And then I will pick what I say so that the way that I imagine they will interpret it is close to what I want to communicate. Right, so in this case, the speaker says some and not all because they imagine that the listener, how do I want to say that? They imagine that the listener, upon hearing some, will correctly infer that they mean not all. Okay, so rational speaker model has been done a bunch of times in NLP over the past decade, probably longer. It generally follows this structure that I've laid out here. So the speaker has to have a model of the listener, right? So we're going to train some model of a listener. So this is going to be something that interprets utterances. In our case, this is going to be an agent that navigates given an instruction. So the listener is going to hear what's said, and they're going to execute the path described. And then we're going to train a speaker to generate utterances. So this is going to be the thing that takes the path that it's trying to describe and generates a language expression that describes that path. And so then at inference time, we'll generate a bunch of samples from the speaker. So the speaker describes its path in 100 different ways. And then we run our listener model on each of those. In this case, we have a little navigator model. We execute the navigator model on each of the possible samples that came out of the speaker. And then we look for the sample under which the listener model executes a path that's as close to the desired path as possible. And then that's the one that the speaker ends up uttering. Okay, so we did this. And we put this in front of a bunch of people and we said, okay, here's an instruction to be followed. Walk down the stairs and wait on the red rug. So this is generated by some model. And then people have this interface through which they can navigate. So in this case, I was doing it. First, you have to find the stairs that go down. And then you start going down the stairs. And then voila, you get really happy because you see that there's a red rug and you're like, I must be doing it right. And then you stop and then you would hit submit. And so the other thing that we do is we ask the participants to count how many mistakes were in the instructions. So this is things like, you know, it said there's a sofa, but there's no sofa, or it said turn left, but you actually had to turn right. How many times you had to guess where to go next, and how easy it was to follow. And the mistakes counter and guesses counter were really designed based on our own attempts at following these instructions and observing what went wrong most frequently. So it turns out that if you do this sort of standard approach that I just described, in terms of human success rate, so this is given an utterance generated by the speaker model, which is, I should have said, it's a fine-tuned GPT-2. How often does the human succeed at getting to the correct final location? So in this case, we're not measuring path similarity, we're just measuring, do they get to the correct final location or not? So if you give them an instruction written by a person, they get there like 90-something% of the time. If you just fine-tune GPT-2 in sort of the supervised learning way, it's about 38% success rate. And if you use this listener model that I just described, it's also about 38% success rate. So that was not super exciting. We also measured this NDTW metric, which measures path similarity, not just success rate. Again, the similarity for the human instruction is very high. The just fine-tuned GPT-2, the orange bar, is substantially lower, and actually the listener is even worse. So people's paths are less like the ground truth paths using the rational speaker model than just supervised fine-tuned GPT-2. Similarly, the rational speaker model generates utterances with more mistakes and with marginally lower quality. So this was a little bit disappointing. And there were basically two reasons why this didn't work. So these are sort of obvious, but the first thing that could go wrong is a listener underscores a correct utterance. So it can't follow the correct utterance properly. Or the listener overscores an incorrect utterance. So it gets an incorrect utterance, but like by chance or by overfitting or something like that, it manages to succeed anyway. So this first one you can potentially solve by just getting more data. So as you get more and more data for training the listener, its score for the correct utterance should just go up. The second one can't be solved by just getting more data. This is really fundamentally a covariate shift issue, where the listener is trained on human-generated utterances, but then it's used based on system-generated utterances. And so getting more training data won't necessarily help here. So this is essentially an overfitting type issue. And when I see overfitting, you know, I think an obvious thing to do is to say, well, let's try some ensembling. So instead of having a single listener, we're now going to have 10 listeners that are trained by bootstrap resampling. So they all have their own idiosyncrasies based on what subset of the training data they saw. And the hope is that whatever idiosyncrasies there are that cause this weird overfitting behavior wash out when you average over a bunch of listeners, either sort of using a mixture of experts or product of experts. Okay, so as you might guess, this works, otherwise I wouldn't be talking about it. Here I've just added the ensemble listener to the bottom. So in this case, in terms of success rate, it consistently improves on the no listener model and the single listener model. The human paths are more like the desired paths. It generates instructions with fewer mistakes, and the instructions are generally of higher quality. There's still a big gap between the ensemble listener and the human instruction. And you can ask, well, if you make the ensemble bigger, does that close the gap? And the answer is it doesn't seem so. So we use 10 here. We did a few small experiments with I think 3 and 8 or something. And it seems to kind of be asymptoting. This is also something where, these numbers are 100 people going through paths in that simulation environment. So you can't just run any experiment you want. You have to be pretty selective about what you're going to do. All right, so to wrap up, what I've largely been sort of pushing towards in this talk is moving up this chain of communication from models that are trained just based on associations to ones that can refer to objects in the world, and then finally to agents that can infer meanings pragmatically. The astute attendee will have noticed that there was not actually a game in this talk, so I hope you will forgive me for that. But I actually really do think games are a super interesting test bed to think about some of these ideas, and we've actually talked fairly extensively about taking some of these models and playing with them in various text game environments and things like that. So if anyone's interested in trying that, I would be more than happy to talk to you, to collaborate, whatever. Feel free to reach out. That's something that I definitely don't have expertise in, but if you do, maybe there's an interesting opportunity to learn from each other. So we have some successes. So a lot of this has been about asking questions, and we have various ways of trying to ask questions that will provide useful information that benefit the agent. And one of the big challenges here is around figuring out when to ask questions, so you're not just asking all the time. And then we're moving towards sort of bidirectional communication, where the agent can describe its own behavior, the human can describe what they want, and they can sort of go back and forth in a natural way. But quite clearly, we're not all the way there yet. I think there's a lot of interesting stuff to do from here. So there's a real sim to real gap. So like I said, these last experiments were all with real people, which means they're expensive, which means that what you really want to do is you want to sort of pre-train the model in a simulation before you transfer. So one of the things that Lingjun is working on right now is basically a framework to do this, to make it easy for other people to pre-train an agent using utterances generated by this rational speaker model, and then transition that to online experiments with real users. So yeah, this work wouldn't have been possible with all the collaborators, Suda, Khan, Lingjun, and Jonathan. And with that, I'll stop and take any questions people have.
All right, thank you, Hal. That was a fantastic talk. Hal says he doesn't do text games, but you guys should go look at his website as the OG inspiration for the Wordplay website. Okay, are there any in-person questions? Okay, could you please come up? Yes, please. Speaking.
Hi, Hal. Nice to meet you. I'm Hal from CMU, and hi. And just for the context, I also did work on modeling self-mind last year, and we also did navigation, but not grounded navigation. We're collaborating with humans. So really, it's really nice to see this really works with human. And I have two questions about the work. And the first question is that are the listeners affixed during the inference, during the interaction with humans? And the second, maybe related question is that do you consider humans are different? They may also overfit to some kind of a distribution. So do you also consider how self-mind model can handle different humans? Thank you.
Yeah, those are both excellent questions. So the first answer is easy, it's no. So in all of our experiments, everything was fixed. And part of the reason for that was that we were worried about getting enough interactions from a single user to be able to like actually learn anything. I guess this is getting to the second question too, but like to actually learn anything like useful about them. It would be interesting to think about this. I mean, I didn't show the results in the talk, but not surprisingly, we also have results where instead of using an evaluation with a human, you do an evaluation with an automated agent. One thing we found is that actually the results don't correlate very well. This has made life rather hard, and we've been working at like trying to find other ways of doing sort of like quick turnaround experiments that don't require spending $500 on Mechanical Turk. But I think this idea of sort of like different models of different users is really good. So there might be something you can do. So I guess like, I mean, this is sort of introspection, but like having done a lot of these pathfinding myself, my experience is that like sort of over time, you can get better at like learning what to ignore in the instructions, right? So like you learn that like, oh, the model is actually not really good at like distinguishing between a couch and a chair. And so it'll often say walk past the couch when it means walk past the chair. And so you can kind of adapt to idiosyncrasies in the model. But like you really, I mean, I've done probably like 40 or 50 of these, and you have to do quite a few before I think you get like a reasonable like theory of mind of the speaker. So I think this is like a super interesting direction to go. I think it's, I think I would need to either get a bigger budget for running Mechanical Turk experiments or think about ways to like cluster people based on I don't know what. So like for instance, in machine learning explainability land, there's this term that I'm blanking on from psychology, but it's like, oh, need for cognition or something like that. So it's like a property that like some people have, which is like they like to like cogitate over things. And so the type of like machine learning explanation that's good for a person who does that and a person who doesn't is very different. So if you come out with like some like small number of ways of clustering people, maybe you could like keep the sample complexity down that way.
Cool. Thank you.
All right, sounds good. Okay, fine. One more question.
Hey, Hal, thanks for the talk. I'm from Microsoft Turing. I had a question that, I mean, for the second to the last work where you had navigational tasks, right? Did you see agents actually asking for the same information over and over again as in not learning in the start, or maybe later, like a contra of that some information that you wanted the agent to ask to achieve a particular intermediate goal was not being asked? And yeah, so if you have an insight.
It's a little hard to quantify because the way that it's set up is the agent does sometimes get different information if it asks the same question again. The setup is sort of this simulated sim to real where like basically some objects are masked out, and when it asks, for instance, for information about the current location, it will get information about one of the masked out objects, but not others. And so if it asks again, it will then get information about a different masked out object. So it's not necessarily irrational for it to sort of ask the same question twice. I think the direction that you'd like, or that I think would be interesting to go, is for it to like ask more specific questions than just where am I, right? Like, what's that thing on the wall? Or, what's sitting on the sofa or something like that. And then you would, I think, very reasonably expect that it doesn't ask the same thing twice. But I'm pretty sure that it actually does ask multiple times for both current location information and goal location information in like the first few time steps.
Thanks.
All right, thank you, Hal. I think that's about all the time we have for today. So we are now in our ACL mandated lunch break, and we're going to be back at 1:30. We've got 2 speakers in the afternoon. We have Srimai from NVIDIA talking about controllable text generation in interactive environments, and Peter Jansen asking if your agent is smarter than a 5th grader. Indra, yes, dude, it's been so long. It's good to see you. We haven't seen each other in like years yet. Yeah. Remember all the things that I know. Thanks so much. Hoping to remember all of our fun things. That's 40,000 lines. Don't check that. Yeah, so
Yeah, the problem is that like really smooth, less smooth is and this is almost and so yeah. So like why is such a so like really so we started to bring so that right now it's just that we have a rolling things about yeah. Are you? I have so I am a bee. So I mean, yes, I'm oh, you're a vegetarian. Oh, okay. You do? There's a ridiculous place called Veggie Grill. That's I mean, I'm the only one with the actual picture. What's the veggie? Plus, I need a lot of data. You ready to look up? I mean, yeah, this is we like and I feel very nervous of what I can do for activities. We thought it was going to be oh, like this. Yeah, it was going to be like that. So, you know, I've been really interested in exploration for a while, and the world and the Windows sort of structure, but not really the facts themselves of the structure. But like, there's no explanation. Yeah, and they should. Streamline the next one. Structure. Yeah. Yeah, actually. Yeah. It seemed like that is unique. That's way more complicated. The trees are pretty good. They're not super great. All right. So, are you also with her? No, I'm with Andy. And with
Nice to meet you. Yeah, I think Yeah.
All right, we're gonna give it like another minute or so for people trickling back in, and then we'll get started with the next set of invited talks. All right, I think it's time to get started. Okay, Srimai, are you here? Hey, you are muted. Let's see. No, it still shows you as like. I think it's like flipping back and forth. This is weird. Oh, interesting. Okay. Wait 1 sec. I might have to like read this.
Can you hear me?
Okay, I can hear Mark.
Okay, so it's not the room.
I don't. Yeah, it might be issues with Srimai's. Okay, Srimai said she's gonna like rejoin. That's so weird. Mark, you were able to talk, right?
Yes, you can still hear me?
Yeah. Can anyone else talk? Or
can you hear me?
Yeah.
Okay. Yeah, I hear.
Oh,
Is there any like error message when you try to unmute? Maybe there's like a
Like Srimai side. Yeah, maybe I'll.
Hmm.
I'm gonna like. I'm gonna try to like make Srimai.
No, you use the right link, Shime. As a host, can you unmute her?
Yeah. Okay. Wait. We got tech support here. So she's our next speaker, Srimai.
Okay.
She's not able to like unmute, or like it just keeps muting her again. Yeah, it just like keeps flickering back.
Can you speak now? Try now.
You didn't hit yes over there. I think you gotta hit yes to like make her.
Right.
All right.
Hi, can you hear me now?
Fantastic. Yes, we hear you. Great. Okay.
That's it. Yeah, it should work now.
Okay. Great. Okay.
I'll just check.
Sorry about that, Srimai. I don't know what actually was wrong, but I'm glad it's been fixed. Okay. Cool. Now we're on track. All right. Hi guys. It's my pleasure to introduce Srimai Prabhumoye today. She's a research scientist at NVIDIA. She got her PhD in computer science from CMU LTI, and where she was advised by Alan Brack and Bruce. She works on controllable text generation with focus on style, content, and structure, and is exploring the ethical considerations of controllable text generations. She co-designed the computational ethics course, computational ethics for NLP course at CMU. And today she's going to be talking to us about controllable text gen for interactive virtual environments. So with that, take it away, Srimai.
Okay, let me share my screen.
Mm-hmm.
Can you see my screen?
Yep.
Awesome. So hello, everyone. Thank you for having me here. And I'm sorry I could not be there in person. I wish I was there in person to attend the workshop and the conference. So yeah, today I'm going to be talking about controllable text generation for interactive virtual environments. So I think we've already seen in the past few years how controllability is important in real world applications. So for example, style and persona are very important to make personal assistants sound more human-like. And having emotions and sensitivity in the content of responses is very important for building empathy bots. And for FAQ bots, it's of utmost importance that you generate accurate information, and so on for other applications. But why is controllability important in virtual interactive environments? So let's discuss that a bit. So when you have an agent interacting in a virtual environment, that agent needs to be aware of the parameters of that environment and what needs to be generated pertaining to that environment. For example, an agent in the ALF world environment has certain parameters where the environment is made up of rooms of a house and the agent is expected to navigate those rooms to complete a task. Whereas an agent in the light environment is expected to have conversations in a fantasy adventure game. Next, it's very important that the agent grounds its responses in the observations that it sees around itself, that is the current state of the environment. The agent needs to be aware of where it currently is and what it can do at its current time step. And finally, the agent responses can be stylized and the agent needs to fit into its character and persona. So with that, I'm going to first talk about some of my prior work on style transfer. And this is relevant if you want to ensure that agents fit into their character and persona. And then I will talk about my recent work at NVIDIA on using pre-trained language models for knowledge-grounded dialogue generation. And finally, we will discuss how these pre-trained language models can be used for text-based games. So let's start with style transfer. So style transfer is the task of rephrasing the text to contain specific stylistic properties without changing the intent or affect within the context. So for example, in a very casual, friendly setting, you might say something like, shut up, the video is starting. Whereas in a formal setting, you will say, please be quiet, the video will begin shortly. In practice, this problem is quite challenging, and I'm going to mention some of the challenges here. So first is that style is culturally diverse. To give you the example of politeness style, saying words like please to the closest of your friends is acceptable in North American culture, but would be considered rude in Arabic culture. Second is that style itself is subtle. Going back to the politeness style, it is not only about the usage of the words like please and thank you, but it could be expressed in other forms like saying something indirectly or using first person plural forms versus second person singular forms. Third is that it's hard to disentangle style from content. This is needed to ideally get separate representations of style and content so that you can tweak the style and while keeping the content constant and change the style of the source sentence. And finally, there's a lack of large-scale parallel data to perform style transfer. So with these ideas, these are the goals that we set out for modeling a style transfer task. First of all, we want to transfer the style of the input sentence. Very importantly, we want to build a model that preserves the meaning of the input sentence. We also want to build a representation such that it has reduced stylistic properties, but carries the meaning of the input sentence. And preferably, we want an interpretable representation. So keeping these goals in mind, we first designed the back translation technique. And on this slide, I will walk you through the process of style transfer using back translation. You take a machine translation system, which is not trained on any style-specific corpus. You can choose a pivot language of your choice. We have chosen French as our pivot language. You translate the style-specific sentence from English to French. You then use the encoder of French to English machine translation system and encode the French sentence to get the representation Z. Latent representation Z is grounded in meaning and has reduced stylistic properties as it went through a pivot language. You then train two separate generators for each of the two styles. So this is an example of political slant transfer, and the democratic sentence in the input becomes "I'm praying for you, sir," in the Republican form. So we train the pipeline by keeping the Z fixed and training two generators for each of the two styles. The generated sentences are then passed to the classifier. The classifier provides feedback to the generators whether the generated sentence actually belonged to the target style or not. Hence, the loss function of each of the generator is a weighted sum of reconstruction loss and the classifier loss. So let's see which of our goals were achieved by this method. The method was able to transfer style because of the feedback provided by the weighted classifier loss. It was also able to preserve meaning to a certain extent, but not really, because the representation that we create in the latent space is in the latent space, and we don't know if it carries the meaning of the input sentence. The representation does have reduced stylistic properties since we translate the sentence to a different language. And the latent representation Z is, of course, not interpretable. So with these lessons in mind, we designed the tag and generate approach. Here I present an example of the politeness transfer task. We first have a tagger which adds tag tokens at positions where the polite phrases can appear. So in case of politeness transfer, the sentence "send me the data" gets transferred to tag "send me the data" because it expects a polite phrase to appear before this whole sentence. This surface realized form is what we call the representation Z in this model. The generator takes this Z as input and generates, could you please send me the data? Both the tagger and the generator are transformers which are trained from scratch. So now let's see which of the goals are achieved by this tag and generate approach. So first, yes, we are able to transfer the style. This is primarily because the tag tokens are replaced with target style words or phrases by the generator. Second, the meaning is preserved as most of the words and phrases from the input sentence are kept the same. We do build a representation that has reduced stylistic properties because the source style words or phrases are replaced with the tag token. And yes, this representation Z in this case is a surface realized form of this sentence, and hence it's interpretable. We can see it. So here are the results for the politeness transfer task. We measure the performance of models of 4 automated metric. The accuracy measures if the style was transferred to the target style or not. Blue, Meteor, and Rouge measure if the meaning of the input sentence was preserved or not. As we can see, our tag and generate approach performs comparable to other state-of-the-art models on style transfer accuracy, but performs much better on meaning preservation metric. And here are the results on additional 4 style transfer tasks. And in all 4 cases, we have the same observation that our tag and generate performs competitively on style transfer accuracy, but it performs much better on meaning preservation metric. I would like to briefly discuss the limitations of these automated metrics. So Blue, Meteor, and Rouge rely heavily on n-gram overlap, and classifiers can easily be fooled by polarizing keywords. To help us understand this better, we designed a naive baseline. When transferring a sentence from positive to negative sentiment, we just append the phrase, but overall it sucked to the input. And similarly, when transferring from negative to positive, we concatenate the phrase, but overall it was perfect to the input. This simple baseline gets 91.3% in style transfer accuracy and 61.4 blue score, which is very high. And this tells us how ineffective these automated metrics are. Here are some of the examples of the outputs that are generated by our tag and generate approach on politeness transfer task. And as a post-processing step, we try to understand what politeness strategies are learned by our model. So in the first example, our model learns to use the could and would forms, which are considered to be more polite rather than can you or will you. In the second example, our model learns to use the first person plural form rather than the second person singular form. And in the final example, our model learns to apologize. So this was about my prior work on style transfer, but let's fast forward to 2022. And I want to quickly discuss controllable text generation techniques and where we are right now. Specifically, I want to talk about the use of pre-trained large language models for controllable text generation tasks. We know that these large LMs generate fluent and grammatical text. As an example, let's once again look at the style transfer task, which is convert the following sentence to negative sentiment. An LSTM-based fine-tuned SOTA model from 2018 generated this as the output. It's more, but nothing to go was open about 9 p.m. And a large LM in a zero-shot manner generated the following 3 separate outputs. And yes, some of these outputs are cherry-picked, but we can rest assured that even if the model may not accurately perform the task of style transfer, it does generate grammatical and fluent sentences. So we have seen the success of these pre-trained language models on general NLP tasks and classification tasks. But how useful are they in steering the output in the desired direction? Also, language models seem to have a lot of knowledge stored in them due to the large amount of data that they have read during the pre-training phase. This knowledge has also been harnessed to solve QA tasks and classification tasks in a few short manner by providing in-context examples of the task. So a natural question to explore is if this knowledge can be used for controllable text generation tasks and specifically for content-grounded generation tasks that I will discuss in the next section. So now in the second part of my talk, I would like to discuss how we can use these large language models for grounded generation and specifically for knowledge-grounded dialogue generation tasks. So let's talk about that. First, but let me describe how most current knowledgeable dialogue models behave. They have access to a database of knowledge and a conversation history. They retrieve knowledge from this database that is relevant to the current conversation history. And in some cases, the models may have a mapping between the conversation history and the relevant knowledge corresponding to it. In either case, a response generator generates a response based on this knowledge and the conversation history. The issue with such designs of conversation models is that the knowledge retriever will not be able to generalize to out-of-domain topics that are not covered in the database. For example, in this case, the user asks about bacon ice cream, but the database does not have entries related to the bacon ice cream. And this confuses the agent and it does not generate relevant responses. The second issue is that a mapping between the conversation and the relevant knowledge is not always available, and collecting such data sets is an expensive effort. And finally, it becomes difficult to retrieve relevant knowledge when the size of the database increases. So our solution to some of these issues was to propose a multi-stage dialogue prompting framework, which we call MSDP. This framework was designed for generating knowledge-grounded responses. So the inputs to our framework are the topic of the conversation and the dialogue history. The first stage is the knowledge generation phase, where knowledge generation prompts along with the inputs are provided to a pre-trained language model, and the LM is prompted to generate knowledge that is relevant to the topic and the dialogue history. In the second stage, we do response generation. In this stage, response generation prompts along with the inputs, and more importantly, the generated knowledge of the previous stage are provided to the pre-trained LM, and the LM generates the response to this conversation. I'll go into detail about each of these two stages in the next couple of slides. So first is the knowledge generation phase. For this prompting approach, we need a support repository from which we will select some in-context examples for the LM. Typically, this support repository is the train set of the data set that you're using. Since there's no fine-tuning involved in this entire framework, the train set is used to select some K samples. So we select K exemplars from the support repository based on a similarity metric. What this means is that K examples are chosen from the train set that are most similar to the query in the test set. Once the samples are chosen, they are converted to this template form where the text of the last turn is concatenated to the topic of the conversation, and finally the knowledge that is needed to generate the response. These K examples are concatenated to each other, and finally the actual query from the test set for which we want to generate the response is appended to it. Since these K examples were from the train set, we do have ground truth knowledge available for them. This whole thing is passed as input to a language pre-trained LM, who then generates the relevant knowledge for this given query and dialogue context. Response generation pipeline is very similar. We have a support repository, again, typically the same train set of the data set that you're using. We select K exemplars from the support repository based on similarity metric. Once these samples are chosen, they are converted to this template form. We have additional tags over here like system, user, we know that, etc., to add structure to our prompt. The content of the selected samples is then added at appropriate places after the corresponding tags. Note that in this case, the actual ground truth response from the train set is also added in the prompt. And finally, the query dialog context along with the knowledge generated in the previous step is added to the template. This is passed as input to a pre-trained LM who then generates the response. First, let's look at how good the knowledge generation stage is. We perform experiments with the Wizard of Wikipedia dataset, and we compare the generated knowledge with golden knowledge mapped to the conversation. Here, DPR scene is dense passage retrieval system fine-tuned on the Wizard of Wikipedia trained data. And DPR Wiki is also a fine-tuned model, but it has access to the entire Wikipedia to retrieve the knowledge. FKG is knowledge generation model, which is basically a pre-trained LM fine-tuned on the Wizard of Wikipedia data. And the MSDP is the knowledge generation stage of the multi-stage approach that I described in the previous slide. And this is the only model on this slide that is not fine-tuned at all. All the models on this slide are similar in size in terms of number of parameters. So we use Blue, Rugel, and F1 to measure the quality of the generations compared to the golden knowledge. We observe that the DPR, which is fine-tuned on the WOW dataset, is better at retrieving relevant knowledge compared to DPR, which has access to the whole of Wikipedia in the case of the seen test set. But the behavior is exactly the opposite in the unseen case. The fine-tuned knowledge generation, the FKG model, is mostly better than the DPR model, but the MSDP KG is the best in both unseen and the seen cases. Here is the human evaluation for the knowledge generation stage. Human judges are asked to rate the knowledge on a scale of 1 to 4 for relevance and correctness. Since DPR retrieves knowledge from a database, we assign a score of 4 for correctness because whatever it will retrieve from the database is going to be correct. We observe that for a similar sized model, our MSDP framework can generate more relevant knowledge compared to DPR, and larger LMs bring improvements on all metrics, and especially for correctness. Now let's look at the results of response generation. Here we compare our method with PPLM, FCM with DPR, the scene case, that is a conversation model which is fine-tuned on the WOW data, but uses the knowledge retrieved by the DPR model. And similarly, we have the FCM with DPR Wiki model. The FCM with MSDP KG is again a fine-tuned conversation model which uses knowledge generated by stage 1 of our MSDP framework. And then finally, we have our two-staged MSDP approach. We compare the generated response to the golden response on the metrics of Blue, Rugel, and knowledge F1 or the KF1. We observe that the fine-tuned model, which uses the knowledge generated by the stage 1 of our approach, consistently outperforms other fine-tuned baselines, and our MSDP framework achieves the best results. And here are the human evaluation results for response generation for the unseen test set. This is done using A/B testing, where human judges are asked to pick the option which satisfies the conditions provided in the question. For example, while measuring engagement, the human judges are provided with 2 options in a random order, which are generated by the 2 models being evaluated. And the judges are asked to pick the option which seems most engaging given the conversation history. If both the options are equally good or equally bad, then the judges can select the neither option. We observe that our MSDP framework outperforms the fine-tuned conversation model in terms of engagement and knowledgeability. What we also observe is that as we increase the model size, the percentage of times the neither option is chosen decreases. In general, the larger model improves on all the three metrics. I want to briefly discuss how model size affects response generation. As we can see, larger model sizes improves the performance on all metrics, but especially we see this in the unseen case where the gains from using a larger model are higher compared to the seen case. Another thing we observe that generated responses may sometimes partially copy the text from generated knowledge. This is because generated response is highly conditioned on the corresponding ground truth knowledge response pairs in the prompts that are provided, and a similar pattern exists in those pairs. So hence we calculate the ratio of number of tokens that overlap between the knowledge and the response divided by the number of tokens in the response itself. We see that the larger model copies less number of tokens from the knowledge, and overall, in general, the model does not simply copy the text of the knowledge, but rephrases this knowledge to make it relevant and engaging in a conversation. Now you may say, hey, why do you need a multi-stage approach? If the LM already has the knowledge, then why do we need to generate it in stage one? Why can't we directly ask the model to generate the response? To answer this question, we compare our method with single stage prompting or SSDP. We skip the knowledge generation phase in this case. The inputs along with the knowledge generation prompts are directly passed to the pre-trained LM, and the pre-trained LM generates a response. So here is the comparison of the responses generated by the SSDP and the MSDP framework. We observe that MSDP outperforms the single stage approach on all metrics, and we see the highest gains for the knowledge F1 metric. The results confirm that the stage of knowledge generation is very important in the MSDP pipeline. Here is an example of knowledge generated as well as the response that is generated by the various models. So given the same context, the DPR model retrieves knowledge from Wikipedia that is not at all relevant to the context, and hence the fine-tuned conversation model grounds itself in this knowledge and in turn generates a response that is not relevant to the conversation. The smaller 357 million parameter MSDP model generates knowledge that is relevant to the context, but the response generation stage does not really make use of this knowledge and instead generates a generic response. The larger 530 billion parameter model, on the other hand, generates knowledge that is relevant and a response that is knowledgeable, relevant, and engaging. So now that we have seen that the knowledge from pre-trained large LMs can be harnessed for generating knowledgeable dialogue responses, the next step is how can we translate this to interactive virtual worlds? For this, we turn towards the Light dataset. Light is a fantasy adventure text-based game which is primarily in the dialogue form. It has a rich environment where agents are provided with a setting indicating where they are, whether they are in a stable or a castle or on a beach and so on. The agents know their own persona, and the environment provides objects to the agents which they can interact with and perform actions with them. But mainly the agents need to have conversations that are pertaining to the environment. Here, we need to ground the responses in these attributes, and the knowledge in this case can be the setting and the persona of the agent. So we have only preliminary results that indicate that this is a promising direction. We show F1 score for zero-shot performance of different Megatron models with varying sizes. The generative transformer is described in the light paper, and it is a fine-tuned model which is only shown to understand how far we are in performance compared to this model. We see that the zero-shot performance of the largest 530 billion parameter model is comparable to the fine-tuned generative transformer. And so it would be good to extend this to a few-shot setting and see how much we can leverage these LMs for the light setting. So with that in the background, and it was a quick glimpse with some very exploratory results on how we can use pre-trained LMs for virtual environments. So now let's see how these techniques can be extended to text-based games. In this work, we focus on the AlfWorld setup. AlfWorld is an interactive text-based embodied environment. It is a simulator that enables agents to learn abstract text-based policies and execute goals from the Alfred benchmark. It's basically the text simulator of the Alfred setup. I have provided an example on the right from the AlfWorld paper. This setup has tasks that the agent is expected to complete. For example, in this case, the agent needs to put a pan on the dining table. The agent is initially provided an observation about the room they are in and what they see around. The agent is then expected to move in that room and interact with the environment. Like in this case, at some point, the agent will pick up the pan and then put it on the dining table. This work is done in collaboration with Yue Wu and Tiffany from the machine learning department at CMU. So to solve this task, we use imitation learning framework. We basically learn a policy using a transformer to choose the action. Very importantly, we use the embeddings of the task to be solved, the current observation and the previous observations. We have an attention head that focuses only on the task to be performed and calculates the probability of the actions to be taken based on this attention. So the task attention head was our baseline, and there are still many challenges surrounding task completion in this setup. Typically, there are many locations that the agent can visit within a room, and the agent can keep revisiting the same location after a few steps. There are also many objects at any one location that confuses the agent. To mitigate some of these challenges, we propose the use of knowledge about the objects and where to find them. Let me demonstrate this with some examples. So here is an example where we can use knowledge to determine which locations need to be visited. Suppose the task is to put a pan on the dining table, but the possible locations that you can visit in the room are stove, cabinet, microwave, fridge, and the dining table. If we have some prior knowledge, then we can safely assume that the pan will not be in the microwave or the fridge. Hence, we need not visit these locations at all. Similarly, we can use knowledge to determine what objects are useful or not useful to complete the given task. For example, if the task is to wash a potato, then our first step is to locate a potato by visiting, let's say, a cabinet. But when you arrive at the cabinet, you may have multiple objects to pick from, like the knife, a pan, a tomato, a bowl, and the potato itself. Now we know that we don't really need a tomato or a pan or a bowl to complete the task of washing the potato. So we can safely ignore these other objects and only pick the potato. So for this, we use knowledge from pre-trained QA systems to determine if the objects are useful for task completion and what locations we need to visit. So as shown here, we ask the Macaw system, which is AI2's pre-trained QA system, a series of questions to determine basically where to go and what objects to focus on. So here I present the AUC curve for predicting if an object is required or not for task completion. The Macaw 11 billion parameter model achieves an overall AUC score of 75 for this task and 64 for predicting if a location is useful or not. And this is on the train set. And finally, here are our preliminary results on success rate for this task. The Butler model cannot be directly compared to our techniques because it is trained using Dagger, which we don't use in our setup. We observe that the knowledge about objects and locations helps in completing especially unseen tasks, and this direction of research seems promising. So to recap, what we have shown is that a single pre-trained LM can be used for knowledgeable dialogue generation. Our MSDP framework can produce context-relevant knowledge and generate engaging and knowledgeable responses. Larger LMs consistently improve the generation correctness and response relevance along with knowledgeability and engagement. We can situate pre-trained LMs in textual games and ground on the environment and the observation. We can also harness the knowledge in pre-trained LMs to navigate and solve tasks in textual games. So with that, I'm open to having any questions.
That was a really good talk, Shima. I had no idea you were working on AlfWorld or any of that, like second half of the talk. I think like I've gotten like 4 messages while you were doing that of people being like, did you see that? I think we're getting scooped. Like, so, okay, cool. Are there questions from the audience in person? So, while people think of questions in the audience, I had a question of my own. Actually, instead of all the AlfWorld stuff, which we should actually definitely talk about at some point, for the SSDP versus MSDP stuff, like, so how much did you actually notice the multi-stage helped as the sizes of the models got bigger? Was there relatively more performance gain of doing multi-stage for the smaller models versus like, I'm assuming the 530 billion is the Megatron Turing LM?
Yeah.
Okay.
But I think the results I showed for SSDP versus MSDP were not on the Megatron Turing LM. It was on a smaller 357 million parameter model. So I don't think we we didn't scale that experiment to 530 billion and see if like there were more gains or not. But overall, what we observed was that the knowledge generation phase, I think, has the highest gains when you kind of go to a larger LM. And so that stage will improve a lot, like, and hence like MSDP would do better than SSDP.
I see. Okay, that makes sense. So sort of like continuing that, I've never actually had a chance to try anything that big on something like light. And I don't know if you've been keeping up with Jason Westman's work, but they had a paper recently showing that persona like dialogue models have a lot of trouble actually maintaining persona. Did you notice that like the sort of a personality conditioned on the sort of the light persona descriptions got any better with the Megatron versus the smaller models?
So actually that is also like a little bit work in progress, and I have only done experiments with 0 shot, so there's like more analysis and more experiments to be done there with few shot. And then yeah, I did see that the paper that you're describing about kind of checking whether there is like consistency in the persona, whether whether the responses actually stick to the persona or not, and those kind of analysis, we are still not at that stage to do that kind of analysis, I think, like, because we haven't done the basic thing itself. Like this was just most of the previous work on light in the past few years has focused on like retrieval systems and like, retrieving the responses. And now with these larger LMs, I think it's moving towards generating responses by conditioning on persona or the setting and so on. And so, yeah, like we are still doing the first set of experiments, I would say on that setting. Yeah.
Fair enough. Yeah, I'd love to see your guys' results on that. Okay, cool. I think with that, we're slightly over time. So thank you again, Srimai, for the talk. And so now we're going to have our last talk for the day and our in-person talk. We have Peter Jansen here, who's an assistant professor at the School of Information at the University of Arizona. And he is going to talk about how we can teach models to perform question answering while generating detailed human readable explanations for their answers. So when he talks about science, you know it's legit because he used to be a physicist, an actual science before he came to computer science. So take it away, Peter.
Oh, thank you. I've never been called a legit scientist in my introduction before. That's very funny. It's even funnier. My PhD is actually in neuroscience, so maybe I'm keep the joke going a little bit further. It's so funny. Can you see? There we go. Yeah. Okay, excellent.
I think I pinned Srimai, so I'm gonna like change it so that.
You can see me both here and directly beside me. Double Peter.
I will just make this smaller because
yeah, sounds perfect. Otherwise, it's Peter's all the way down.
Yes.
Cool. Thanks for that introduction. I, like many of you, have been teaching hybrid, and so I'm into the pen these days. So yes, I'd like to talk about this really cool project that we've been working on for the past year or so called Science World. Is Your Agent Smarter Than a Fifth Grader? This is cool work with great people. Rhea Wang, who's a fresh PhD student of mine, Mark Alexandra, who's one of the organizers here, and as well as Raj, who just introduced me, who we're sort of joking over lunch. I had a paper that was rejected. And one of the reviewers wrote back, it cites Amana Bralu way too many times. And I'm like, I think that they thought that I was him. But I think because he's written a double-digit percentage of the entire literature of the area, we're kind of in that situation. So pick your top 5 Raj papers to cite whenever you're working on anything these days, is I think the thing to take away from that. So anyway, moving on here. So this project describes a text game for science, for learning, for evaluating our agents' abilities to basically think like a 4th or 5th grade elementary science student. So the same stuff that a 4th grade elementary science student is tested on standardized exams in the United States is what our text game tests, which is kind of awesome. These science exams have been used for about 5 or 10 years by the ARC team or the Aristo team at the Allen Institute for Artificial Intelligence as a challenge task. I remember working as a postdoc on this task, sort of banging my head against the wall, trying to get performance to go up, and you'd sort of get up maybe 1 or 2% per year. And then large language models came in and absolutely just felled this benchmark. And the latest models can get an A on these exams. So it's really impressive. And so this work is basically trying to test to see, okay, can these language models that are answering these standardized science exams, are they actually understanding what's going on here? Or are they just sort of parroting back responses, which I know many of us are sort of concerned with. And so we're testing them on the same knowledge, but in a different way. Instead of testing them on sort of multiple choice questions, we're testing them on questions that are situated in the environment and they present in slightly different ways and whatnot. So just sort of to ground this as an example, since it's probably been a while since many of us were in 4th grade, here's an example of a elementary science question. Which of the following is a good conductor of electricity? a metal fork, which is of course the answer, a plastic spoon, a rubber boot, and a wooden hat. And the thing that's of course important here is the material that it's made of. So we're interested in testing robustness. We're interested in inference, the sort of scientific and world knowledge that comes with having to solve science exams. I'm going to do something that I almost never do in a talk, and I'm actually going to give you a second completely different motivation for wanting to do this work. So I'm a question answering guy, but I'm also kind of a research methods guy. And the specific kind of question answering that I work in is sort of this multi-step question answering, where you can't just directly look up an answer. You have to sort of make an inference by putting a whole bunch of different facts together. In fact, in elementary science, we know that you need an average of about 4 to 6 facts to answer the question, and as many as 16 different facts from a knowledge base to answer it. So it's quite a bit. And so as a research methods guy, I've sort of put a lot of work into making lots of multi-step gold explanations for science exam reasoning, but we have this problem. Our models are getting so good at doing multi-step reasoning that they're creating explanations that are wildly different than the explanations that are in our gold data, but they're still good. This is something I never thought I would see, or at least I thought that I would have more gray hair when I did see it. And so we have this problem, this evaluation problem, because normally what we do is we say, okay, how well did we generate the explanation? Well, we could either pay a bunch of graduate students to go through and evaluate these, or we can do it automatically in a second, right? And so we do it automatically in a second most of the time by saying, what's the overlap between these two explanations? The problem is there's no overlap. So our automatic evaluations say your model is doing terrible, when in fact it's doing fantastically well, right? And so the way that I've honestly gotten into text games and why I'm here today is because I think, and I believe, and in fact, this is what this talk is about, that we can use text games and the action sequences that we have to perform in text games in order to sort of more objectively evaluate the reasoning of something. If your task is to boil water, it doesn't matter what explanation, what textual explanation you gave, that what matters is, did you boil the water or not? So it's sort of an objective way of measuring these things. So just to give some context about how great language models are, here's GPT-3. We've seen this a bunch today and certainly this week. Is a metal fork conductive? Yes, a metal fork is conductive is what it says. So GPT-3 language models seem to know something about elementary science, right? And they also seem to have some procedural knowledge that you could convince yourself that they might be pretty good at actually performing these experiments in a text game about elementary science, right? So how could you use a battery and a light bulb to test if a metal fork is conductive? This is what our first question is about. Well, the battery and the light bulb could be used to test if the metal fork is conductive by using the fork to connect the positive and negative terminals of the battery. If the light bulb lights up, then the fork is conductive. Sounds pretty good, right? It sounds like it might know how to do this. In fact, if you connected the positive and negative terminals with the fork, it would catch fire. But other than that very tiny, small issue, this is pretty darn close, right? It's 90% of the way there. In fact, that's actually an unofficial theme of this talk, is a lot of the time it just wants to catch things on fire, which is funny. And so normally I need a little bit more of an introduction to this, but I think of all venues, I probably don't need to introduce what a text game is here today. So the vehicle we use for this is, of course, text games. So the idea here is that the game is rendered entirely in text, as it is here in Zork, which is on Raja's shirt. And so you start off being cued with something. You're standing in an open field west of a house. There's a small mailbox here. You give it textual commands, open mailbox, and then it tells you what you did and whatnot. There is no, it might surprise you to learn, there is no existing text game that tests elementary science. And so we had to make one called Science World here. And we didn't just have to make the game, but we had to make the simulator for it to accurately simulate all the kinds of interesting scientific things like thermodynamics, electrical conductivity, and whatnot. The environment itself looks something like this. Well, it looks nothing like this because it's in text. So we drew this nice picture so we could actually talk about it entirely. And it has 10 rooms here, things like the kitchen, the bathroom, the bedroom, the workshop, the art studio, a greenhouse. This is probably something most of us don't have at our homes, a foundry, but there's lots of elementary science questions about melting metals and things like that. And we kind of had to ground it a little bit. To give you a little bit more solid numbers here, there's 10 of these rooms and locations. There's 200 objects in our simulator. So it's a pretty good size simulator, things like a sink, paint, a light bulb, and so on and so forth. One of the things that distinguishes this simulator amongst others is that basically everything in it is modeled at a level that you just don't get to see most of. So like there's chocolate in the simulator. How many of you know what the boiling point of chocolate is? I had to figure that out so that we could, yes, exactly. I had to figure that out and look up very strange literature that I've never had to use Google Scholar to find previously in my life, to find the melting point of chocolate, the boiling point of chocolate, the combustion products of chocolate and whatnot, so that we could build a simulator that was high enough fidelity so that when an agent goes in and tries to do all these interesting experiments, that it will generate things that are pretty close to what would actually happen. And along that path, there's sort of these other devices and things that you can use, heating things like stoves, cooling devices like fridges, thermometers, stopwatches, and other instruments. So that's the beautiful picture. Let's show you the actual text of what this actually looks like. So here's one particular task. I'll explain a lot of the different tasks later. There's actually 30 of these things. But this task here is to determine electrical conductivity of an object. And the specific object that we're going to determine the conductivity of here is aluminum foil. It tells you a couple things, like the aluminum foil is located in the workshop. First, it asks you to focus on the aluminum foil. That's something that we do in this environment. We want our agents to act intentionally rather than just sort of choosing random actions. So sort of like a game of billiards, you have to call out the action or the object that you want to interact on beforehand. So like 8-ball in the side pocket, you want to say, I'm going to melt, or I'm going to test the conductivity of the aluminum. You probably don't want to melt it. How do we get it to answer? Well, there's lots of different ways. In this particular task, if the aluminum foil is electrically conductive, you put it in the red box. And if it's non-conductive, then you put it in the green box. And so away we go. And I'll just kind of buzz through this pretty quick. The first action is usually looking around. It turns out that we're in a place called the hallway. This is sort of rendered in a little bit of a list form rather than a narrative form like you might see in Zork. And we see the hallway is actually pretty bare. It does have a picture in it that you can look at if you want to, but it has lots of other places that you can go. And in fact, we're lucky because the workshop is pretty close. So we'll open the door to the workshop, and it actually notes that the door is already open. These paths, by the way, were made by a bot. We include agents that run through these gold paths in our distribution. So then we're going to go into the workshop, then we're going to pick up the aluminum foil. We're going to focus on the aluminum foil to say that's the thing that we're going to measure the conductivity on. And then this is where it gets kind of interesting. How do you measure the conductivity of something? How do you know if it's electrically conductive, right? Well, if it's aluminum foil, you know that, right? You don't need to go and measure it. But say we wanted our agent to measure it because it's an unknown substance. Well, you could go get a multimeter and measure it, but we don't have a multimeter in the environment. And so another way of doing it is making a multimeter by basically taking a bunch of, a battery and some wires and sort of connecting it up to the object, like the aluminum foil here, and also connecting it to, say, a light bulb or another kind of actuator and seeing if it turns on. And if it turns on, it's electrically conductive. If it doesn't turn on, it's not conductive. And so we have that here. We have a battery, we have a purple light bulb, we have a bunch of other wires on here. There's even a switch. There's motors and other things. These are, by the way, parametrically generated. So every time the environment generates, you get a different subset of stuff that you can build your circuit with. This is the boring part. I actually have, I postdoced in electrical engineering for a while as well, and I'm glad that I didn't learn electrical circuits this way. But you build a circuit step by step, connection by connection. So connect the battery anode to the black wire terminal 1, connect the battery cathode to another wire, connect one end of the black wire to the light bulb, and so on and so on. I won't bore you all with making electrical circuits. And then after you're done making, doing all the connections, what you basically do is you look and see if your actuator is doing something. And here the red light turns on. That means the aluminum foil is conductive. What do we do if the aluminum foil is conductive? we move it to the right box. So we move it to the red box and it says you move the aluminum foil to the red box, task completed, done. That's one of our 30 tasks, testing the conductivity of objects. Now, under the hood of Science World is probably the most high fidelity text-based simulation ever made, which is sort of a very weird thing to have to claim. But we have thermodynamics engines for simulating things like heat transfer, combustion, thermal conduction coefficients, phase changes, so changing from solids to liquids to gases. The engine here is so wild that you could light a piece of paper on fire, put it in a cupboard in the kitchen, and it will ultimately burn the entire house down. It just like, it's very high fidelity. There's an electrical simulator in here that simulates simple series circuits. We have lots of polarized and unpolarized components, lots of conductors and whatnot. There's a chemistry engine for lots of different kinds of chemical reactions that are common in the elementary science curriculum, making salt water, rust, paint mixing, and things like that. Life stages, so plants progress through life stages. They can ultimately reproduce. They tend to need pollinators in order to transmit genetic material. We do simulate Mendelian genetics, so your plants will inherit traits based off of each other. And then sort of this last one here, which is kind of different than all of the others. What's a good way of putting this? Science and the science curriculum is inherently very spatial. A lot of the questions are things like a planet is orbiting around the sun, or, you know, a cart is traveling down an inclined plane or something like that. And space is obviously the thing that we don't simulate very well at a very high fidelity with text-based games. But we still wanted to include that in here somewhere. And so we actually have an inclined plane experiment where you can sort of put things on an inclined plane and watch them slide down, and it tells you roughly how far they are, so that you can measure things like the friction of the plane or the friction of the object or angle of the plane and so on and so forth. And there's a few other simulators that are slightly less interesting. So we have 30 different tasks across the most common curriculum topics that you find in elementary science. We have changes of state, melting, boiling, freezing, measuring things, particularly temperature, building and using electrical circuits, object classification, this is probably the simplest one, plant life cycles and their pollinators, mixing things, lifespans and life cycles, friction experiments, and then one of my favorites because it's so ridiculously hard, the Mendelian genetics experiment. Before I sort of dive into some of the specifics a little bit more, I want to talk a little bit about task variations and sort of parametric variations. So a lot of the research methods problems that we sometimes have with text environments is that you train and test basically on the same environment some of the time, right? Which is a bit of a difficulty because you're going to overfit to that environment. And so here, to prevent that, each environment has a bunch of parametric variations. So we vary it in two different ways. The first one is that the environment itself is parametric. And so one time you generate it in the living room, you might have a bookshelf that's got 3 random books like Moby Dick on it that you can actually read. Another time the bookshelf might be empty. Another time you generate it, there might be a table instead of a bookshelf there. So there's environment variations. But then we also, more critically, vary the task, the critical task objects here. And so, for example, for the change of state task, it'll vary the substance that you have to melt or boil or freeze. So one time it's water, the next time it's, oil. For electricity, we vary the kinds of components that you have. One time you have a motor and a blue wire, the next time you have a light bulb and a red wire or something. Or plant growth, the different kinds of seeds that you have to grow, and so on and so forth. And so in this way, we can assemble sort of proper train development and test sets for this environment. I'm just going to buzz through this part very quickly here. We have a lot of different tasks, and I'm going to try and ground what those 30 tasks are. In this slide here, or in these slides here, it describes both the number of subtasks for each curriculum topic, but also the number of variations that we have, which are parametric variations, which is quite large, just to give you a sense of sort of the scale here. And so for changes of state, you have to melt, boil, or freeze something, or you get a free choice for any phase change that you want to make. That's actually one of the hardest things any of the agents find for this. For the next task, measuring temperature, you either have to measure the temperature of an object or you have to measure something's melting point or boiling point. I will say that these are kind of interesting in that they give us a clue about some of the methods that we use for response in our text game. You might want to say, you know, okay, I'm going to measure the temperature of the apple, and the apple is 30 degrees Celsius. And so I want the agent to write the apple is 30 degrees Celsius or whatnot into the console. The problem with that is that it ups the complexity of the model that you would need to use to solve these. And we wanted to keep it simple. And so some of these tasks we model as forced choice tasks. And basically the way that we do that here is we say, measure the temperature of the apple. If it's above 50 degrees Celsius, put it in the red box. If it's below 50 degrees Celsius, put it in the green box, and make various parametric versions of that to be able to model it as a forced choice task. Some of the other things that we do here is pairing tasks with named and unnamed variations of this. What I mean by that is we might say, measure the melting point of water. We all know the melting point of water, right? That's something that we learn, and conceivably that's something that an agent could look up in a knowledge base, which would be fantastic and a really cool result. That's kind of cheating, but it's a kind of cheating that you want the agent to do because we should all have knowledge, right? We shouldn't wander around needing to learn everything from scratch all of the time. In order to test whether it's using knowledge from a knowledge base or whether it's actually performing the experiments, we have variations of tasks that basically mask the critical task objects. So instead of saying water, it will say unknown substance J, measure the melting point of unknown substance J. And so you have to actually perform the experiment to do it. So again, I'm going to buzz through these. Building electrical circuits, you have to use renewable and non-renewable energy. Some of the time you need to know that a solar panel needs sunlight to work. Object classification, this is probably the simplest task that we have. One of them will be one example is find any non-living thing and put it in the red box in the kitchen. And so our agents are the best at that because it's pretty simple, sort of a pick and place task if you're thinking from sort of the Alfred data set. Plants and pollinators, you need to grow plants from seeds, you need to use soil, you need to use water, they need to be in a container or outside somewhere. Cross-pollinating plants that produce or reproduce sexually in order to produce fruit. Chemical mixtures, so common mixtures as well as paint, secondary and tertiary colors, almost done these. Lifespans, so the longest, shortest, or longest then shortest animals. So for these examples, it'll say something like, there's 3 animals in the environment, focus on the shortest lived one, or the longest lived one, or the shortest then longest. And so you'll go through the environment and you'll see a turtle and a chickadee and a field mouse, and you'll have to focus on the turtle because that one's the longest lived. And then sort of the last ones here, the friction ones. So you need to identify the angles of planes or things of that nature. And then the ridiculous one, the Mendelian genetics one, where it basically replicates Mendel's original genetic experiments that happened with pea plants. And so you need to determine whether given traits are dominant or recessive, so like flower color and whatnot. And you can do this either with the pea plant itself or with randomly generated plants as well. So scoring and reward shaping. So how on earth do we measure the progress of this task here? So we have both required sparse worth large reward sub goals here as we see up here. So the task is, this task example is, your task is to boil water. First focus on the substance, then take any action that will cause it to change its state of matter. Our required sub goals here are the agent simply has to focus on the water, and then at some point they have to change it from a liquid to a gas. They have to boil it. We don't want to bias our agents to solving a task in a particular way because there's lots of different ways that they could do it. This goes back to those very first slides. You can think of this as different ways of explaining how to do something, right? If you wanted to boil water, you could go and put it on the stove, or you could go and build a campfire and boil it that way. And so we don't want to bias our agents to doing it in any particular way. We just want them to do it, and then we're happy. However, because it's reinforcement learning, as many of you know, if you don't leave breadcrumbs, then the models tend not to do particularly well, right? And so we have a variety of denser optional sub-goals. They don't need to do these things, but if they do them, it will give them a tiny little reward to help them. And so these include, for example, here, being in the same room as water. It's always a good idea to be in the same room as the object you need to work with. Having water in some sort of container like a cup, activating any of the heaters, having a lighter in the inventory in case you want to start a campfire, heating the object by at least 20 degrees Celsius so that you don't start heating the object and then the agent just decides, no, that's a terrible idea, I'm going to start doing something else with it, and so on and so forth. And then ultimately, all of these test scores are normalized to between 0 and 1. Okay, how big is our action space? We've heard people talk about action spaces these days. So we have 25 actions in Science World, and they include sort of the normal kinds of actions that you'd expect to see in most space environments. So things like opening and closing, looking around, reading, picking up and putting down and whatnot. But they also include some science-specific actions that you don't really often see, like connecting or disconnecting electrical objects, mixing things, and so on and so forth. And so if you imagine all of these sort of slots for the objects in these action templates, and you imagine that we kind of have about 200 possible objects, you can naively estimate that for a given step in the environment, we have about 200,000 possible action object combinations. So the action space is actually quite large, even though, of course, most of those actions would not be meaningful for a given task at a given time. But it's if you just sort of use a random agent, it's not going to find this. Just to compare that very, very quickly to 3D simulators up here, grid world simulators like NetHack down here, and then other text-based environments. So in terms of 3D simulators, if you're talking Alfred or Minecraft, typically they mostly have move actions, particularly in the case of Minecraft, the Momo wrapper, and only one sort of interaction action. Whereas for something like Zork, you have 56 commands, but in general, most of these others have many fewer actions, right? And so we're sort of sitting, Science World is sort of sitting at about half Zork complexity. I don't know that we formally measure things in Zorks, but maybe that's a thing we can start right now. Okay, so I've set up the environment. We know that we have this Science World environment. We know that we have 30 tasks. We know that we have experimental methods to run a bunch of different things. Let's get to the modeling part of the talk. So we set up simulations or experiments, I should say, with 5 sort of common baseline models that we could get running for this environment to see how well do contemporary models work at solving elementary science. The first model, and by the way, I'm just going to briefly introduce these if you're interested. There's lots of literature on them. The first model is the DRRN, or Deep Reinforcement Relevance Network. This model here is sort of like the base. It's sort of like the TF-IDF model of text worlds. It performs shockingly good in spite of its simplicity, and it's state-of-the-art or near state-of-the-art on a lot of environments. And basically what it does is it just keeps separate embeddings for the state space and the action space. And then it tries to learn a policy that maximizes the reward for the task that it's learning. The next model, COM over here, is very similar to that, but it uses a GPT-2 language model to try and pre-generate a list of likely actions that it ought to take at a given time. So it generates a short list of actions given what it's currently seeing in the environment, and then it uses something like a DRN to try and pick which action to take. The next model here was written by Raj, and it is KG-A2C, and it uses an actor-critic architecture to sort of build a knowledge graph about the world as it's interacting with the world, and then uses that knowledge base to further its task performance. And then, because the model or the tasks or the talk sort of started introducing language models, and can large language models do as well as they do at Science World as they do on science exams? We use T5, or more specifically Macaw, which we saw in the last talk. And Macaw is a variant of T5 that was pre-trained by AI2, and this performs very, very well at those science exams. We get about 90% of the science exams questions answered correctly with Macaw. So nominally, you would expect, if you know how to do the science exams, maybe you ought to know how to do the same thing if it's presented slightly differently, right? We try this out in two different flavors. One is behavior cloning, and one is a decision transformer. And just sort of really briefly, the difference between these is whether they have a notion of the expected reward or not. So both models are queued with the task description, the current observation that they're seeing, the previous observation that they're seeing, the previous action. So it's sort of like a Markov model with a look back of one. And then the decision transformer also includes a notion of how much reward is left to be won in the task. And I should say that while these other, or while the earlier models that I talked about basically don't have training data from the environment, they don't generally use gold training data, these T5 models have extensive training data that we provide. We provide about 200,000 gold action steps in the environment to pre-train them on. So they not only know how to solve 90% of elementary science questions, but they also have 200,000 steps of pre-training on how to solve exactly these kinds of tasks. You can tell I'm really setting this up, right? Okay. Let's make the splash then. So here is our results table. You probably didn't bring your binoculars. And so I'm going to orient you to the table, and then I'm just so that you understand what the flavors are. Don't try and read any of the numbers, they're tiny. And then I'll show you a summary table. What we have here is, if you struggle reaching your 8-page limit for your long paper submissions, you can use 1 page of that in your Science World papers for just the results table. So on this long axis here, the y-axis, are the 30 different subtasks that exist in Science World. So changes of state are up here, using thermometers and other instruments are up here, electrical conductivity and so on are up here. On the x-axis at the top, we have the different models that we tried out here. The first one is just sort of a random baseline. We have the deep reinforcement network, Raj's knowledge graph, the COM model, that's GPT-2, and then the 2 transformers. Here is the summary of the average performance, basically down these sort of numbers down here. And what we see, remember these numbers are normalized between 0 and 1. So 0 means the model makes no progress on the task. 1 means it solves the task. In general, what we are observing is that the models are not able to do very well at these at all. So a random baseline can get about 3%, and most of that is from just 1 or 2 easy tasks. The deep reinforcement relevance network is getting about 18% performance. And then most of the rest are actually quite low. And we've been tinkering with this since the preprint came out to sort of expand this with either larger models or larger input links and whatnot to try and push these numbers up a little bit. And while we've been able to get them up just a little bit, it's still about the same story. So the overall performance is very, very low with these models. So this is a difficult challenge task, even though when we frame it as a multiple choice question answering challenge task, the numbers are 90%. When we reframe it as this interactive text game, the exact same questions are getting very low performance. So something interesting is going on here. The other corollary to this story is the following. Models that have smaller parameter spaces, so the tiniest models are actually performing better, at least a little bit better than some of the larger models, right? So if our 1.5 million parameter model is performing about similarly to our 11 billion parameter model, it means that maybe there's a capacity that isn't well represented with this model, right? Maybe it's not just the size that matters, but maybe there's something else that's really going on here. Okay, what is going on here? Well, we don't know. But here's a couple of graphs to show you at least a little bit about what's going on. So here's 4 graphs of performance of the different, of 3 different models, not the language models, but basically performance over time for the deep reinforcement network, the CALM model, the GPT-2 model, and the knowledge graph model. And in this case, we have 4 different tasks. The top one here is the easiest task. Find any non-living thing, stick it in a box, not any box, a particular box in a particular location. And so what we see here is that though performance sort of starts out pretty low, there's sort of this general trend that they kind of sort of figured out. I think the models are generally getting stuck on sort of navigation tasks and whatnot, but other than that, they seem to get the general sense of things. Very hard tasks like perform any change of state, it seems like they just are completely out to lunch. They just, even with 200,000 training examples, they're just not getting this. The DRN model, that simplest model, is the only one that gets a non-zero performance, and its performance is only 3%. And then similarly, something that's sort of weird, that's mostly to get you interested in this rather than to provide an explanation, is the set of paired tasks down at the bottom. These tasks are testing the conductivity of substances. This one, we give you the substance name, like aluminum foil. This one, we just tell you unknown substance J. And what we see is that the performance is overall quite low. It's about 10% maximum when we give you the name. When we don't give you the name, something else kind of interesting happens, and the DRN, the simplest model, is actually able to perform better. So there's lots going on here, and it seems like an interesting instrument that we can basically use to ask a lot of interesting questions. What's going on here? Part 2. Well, language models seem to struggle with a lot of these tasks. One task that's not going to be shocking to many of you that they struggle with is the idea of navigation. So if you, for example, queue GPT-3 with a map that's expressed as text. You're in the kitchen, connected to the kitchen is the bathroom in the hallway, living room is connected to the hallway, greenhouse is connected to the hallway, and so on and so forth. And you ask for a path. What rooms do you have to go through to get to the shed? Then it ends up not doing very good at it. It gives you the wrong answer. In fact, you might even say that GPT-3 can't really find its way out of a wet paper bag. This is a real example. It actually told me this. I didn't make it up. But more is going on here. It's not just navigation. If you stick all of this stuff in the same room, it still doesn't perform well. So for example, oops, sorry, where are we here? Here's one where it sounds good, right? How do you make purple paint? This is a mixing task. If you have red paint, yellow paint, and orange paint. Note here, these are not the primary colors that I've cued it with. I've cued it with 2 primaries and one that should be blue paint here. Orange should be blue. GPT-3 gives us a very compelling response. It says you can make purple paint by mixing red paint and blue paint. That's right. It's fixed the error in the input. It's told us what to do and how to do it well. Okay, this is really, going to work. But then if you cue it with the correct cue, how do you make purple paint with red, yellow, and blue? It tells you you can make it by mixing all of the paints together. And that is, of course, going to make some sort of weird brown paint. So, you get the sense with a lot of these models that if you play with them for 2 minutes, you're really impressed, right? Wow, this thing is doing amazing inference. But if you play with them just a little bit longer, you see it's more the discourse that it's getting right, the discourse level things. They sound right. but the content of them, the semantics of them isn't quite right. And in fact, when we test them in this parametric environment to test the same inference in a bunch of different ways, what we find is that they just do not do well at all. And so this is my last slide here. In summary, we introduced Science World, a virtual environment, perhaps the most high fidelity text-based game ever. We've actually got a real flushing toilet in it that connects to a sewer system and whatnot. It turns out when you do science, you have conservation of matter, things need to go somewhere. It's kind of weird. And it allows you to test a text agent's knowledge of 10 elementary science curriculum topics, over 30 tests, and 7,000 different variations. This is the same number of elementary science questions that have been asked in the United States in about the last 10 years. So it's quite large. Science World is challenging. It's hard, and our very best models struggle with basic tasks, even if they can do these well when they're expressed as questions rather than simulations. There's this huge disconnect where we see getting 90% with Macaw on science exam questions, but that we get such low performance on these exams when we do it as a text game. And this is something that you can just get today at this URL. And our framework, like NAACL learning environment, is just pip installable. You can install it in about 2 minutes and away you go. So with that, thanks. And I'm happy to take any questions. Yes.
Hi, my name is from USBC. I have a question. So you see the COM model is like a combination of GPT-2 for service and then combined with the DRN. But it seems to perform a lot worse than just DRN itself. Does it mean that it's doing something else?
That's a great question. So the question, to repeat it. Yeah. So to repeat the question for the folks online, the question is, what's going on with that COM model? Because the COM model seems to be is supposed to be a combination of the DRN and GPT-2, but its performance is actually lower. One of the ways that, so text games are hard. And one of the ways that in the literature we make the problem easier is we give a list of valid actions to the agents that they can choose from. And so you can say, here's all the 1,000 possible valid actions you could take at this moment. The DRN, the sort of vanilla DRN, is given that list of possible actions, and it just has to choose from that list. The COM model, one of its main contributions was trying to use GPT to remake that short list without having to have that handicap. The valid action handicap is what that's called. So if that makes sense. Yes, good question.
Have you performed any kind of error analysis to know where these agents going to fail? What kind of errors do they make?
That's a great question. We're working on error analyses right now, but I don't have any great ideas or any great results to share with you. One of the things that's most challenging about it right now is that the performance is generally so low. We know that navigation is a problem. We know that if you put stuff in the same room, it does better, but that's not the whole story. There's a lot more going on. Who wants to go next? Lots of questions. Fantastic.
Do you have any insights on why the unnamed objects, like the finding the melting point of an unnamed object turns out to be like easier?
Yeah, so that's a really good question. So the question is here. Why does it do better when it doesn't know the name of something than it does when it does know the name of something? It's a very strange thing. When we discovered that in the data, it really is a noodle scratcher. I have no idea why. I can sort of tell myself a story that if you have the name of something, then it might sort of bias it towards one thing or another thing. Whereas if you just have the word unknown substance, you know it's a substance, maybe it's more generic, maybe you could go, but really I'm just pulling straws out of a hat here. So it's a great question. You should write a paper on it. Yes.
Really cool talk. I love this. I wonder if you consider the reverse setup where rather than having the models try to be the agents solving the problems, whether the models could be simulators of the scientific physical interactions that you might have.
Oh, I see. So don't make the models the simulator, or sorry, make the model the simulator rather than make the model be the agent in the simulation. It's funny that you say that. Back up slide number 1. Thank you for the segue. Yeah, I tried to do that for a few years before doing this, and it's way harder. So you can sort of do it exactly in those 2 ways. One, you can do it agent-centric. One, you can do it world simulator. I will run through my 10 seconds of hilarious, this is sort of the outtake reel of this. So there's lots of different ways that you could build a simulator, right? You could go the AI2 Thor route, which is what Alfred has built in. And if I ever get a 50 million DARPA grant, if there's any program managers in here, come see me after, then I would do this. Raj and I have something going on right now where we're trying to do this in Minecraft because it's lowers the barrier to entry. I thought about doing it in NetHack. You get the spatial dynamics, but you don't get the conceptual level simulation, which is really important here. And so I ended up doing it in the text world. Before I did that, I built a grid world to try and do this. So this is a really terrible prototype of science world in a grid world. All of this stuff is there. You have wood, you have fires, you have things to eat, you have trees that you can chop down to get the wood, and so on and so forth. Substances, my art is terrible, you know, copper, magnesium, and whatnot. And then I said, no. Really, I need to do this in Minecraft. The problem is that Minecraft, you don't get at a lot of the nitty gritty of it in order to implement thermodynamics, electrical conductivity, and whatnot. And so I rewrote Minecraft from scratch in Scala, as I sort of had a misspent youth as a game developer. And it turns out this is a really terrible idea because once you get to about 1 million voxels, the frame rate just tanks and there's all sorts of tricks you have to do. And I don't have that time, I have a kid, a 4-year-old. And then the last but not least is this one here where I said, okay, maybe I can just make a simulator by using knowledge bases and writing patterns over those knowledge bases, sort of like queries that make patterns that instantiate in different ways. This one is for melting ice, this one is for boiling ice, and so on and so forth. And so I wrote a domain specific language for this. This was at EMNLP last year or whatnot. Turns out this is also a terrible way of doing it because it's, you know, there's only one person who can program in this language in the world, and I'm not very good at it. So it's just very hard. I think you have to learn the world model. And so what I'm hoping that we'll be able to do is that in order to do well at Science World, the agents will learn how to learn a world model. Then we can plug it into real world. You get where I'm going with this. Yeah. Okay, cool. I don't know if we have time. Do we have time for one last question? There was somebody over here who's had his hand up. Yes.
Yeah. So on the slide where you're showing how GPT-3 is doing on the navigation test, it reminded me that there was a recent paper called Large Language Models are Zero-Shot Research, where they were talking about something called chain thought prompt.
Yep.
We're using a specific prompt phrase, such as let's think about this step by step. They were able to get GPT-3 to increase performance on common sense reasoning tests from like 10% up to 40%. So I was wondering if something like that might also help with something like the navigation test.
That's a great question. So the question is, hey, there was this really cool language model paper that came out about prompt engineering, and it showed that you could do multi-hop reasoning better if you say, let's think this through step by step. Could that help for navigation tests in text world? That's a great idea. I haven't thought of it before. I have GPT-3 open in a browser window. We can meet in the back of the room after this and give it a shot and see if we can come up with some prompts. So it's a great idea. Oh, yeah.
Yeah. A little bit suggestion is that maybe it's too hard to get that quick. So maybe you can control it like without navigation or limit to the just a physical experiment. That way you can see much more insightful results, first of all.
Yeah, that's a great observation. So it's definitely, so the observation is it's hard. And so maybe we could make it simpler in order to make more incremental progress. Science World is modifiable and you can change it without too much trouble. And if it is too much trouble, just make a note in the GitHub and it might be something that's easy for me to change. We do have a huge variation in task difficulty. Some of the tasks are pretty easy, and my suspicion is that those will probably be felled pretty quickly. Whereas other ones like the Mendelian genetics that you actually require kind of a knowledge of statistical mechanics in order to work, that one's probably going to take a little while. My suspicion, though, is that if we can't solve these, that every fourth grade science student could answer these without any trouble. My sense is that this is probably a benchmark that we should maybe work towards, and that then maybe I can make Science World 2. That's a little bit harder. So. Oh,